Imagine for a moment that everything you know about the universe is wrong, that the cosmos is not just vast and mysterious, but filled with horrors beyond your wildest nightmares. What if I told you that the serene night sky you gaze upon is merely a veil, hiding incomprehensible terrors that lurk in the depths of space? Welcome, brave viewers, to Space Mysteries. This is a journey that will challenge your perception of reality and leave you questioning your place in the universe. To truly appreciate the cosmic horrors that await us, we must first confront the staggering scale of our ignorance. The observable universe spans approximately 93 billion light-years in diameter. That's a distance so vast that if you were to count each light-year as a single grain of sand, you'd need a beach stretching across the entire United States, and then some to contain them all. Yet here's the truly terrifying part. This observable universe, incomprehensibly large as it is merely a fraction of what exists beyond our cosmic horizon, forever hidden from our view due to the expansion of space-time itself. Within this unfathomable expanse, we find ourselves perched on a tiny blue marble, orbiting an unremarkable star in the outer reaches of an average galaxy. Our entire recorded history, every triumph and tragedy of human existence, has played out on this cosmic speck. The sheer scale of the universe renders our existence infinitesimally small, a humbling realization that sets the stage for the horrors to come. The concept of cosmic horror taps into our deepest fears of the unknown and unknowable. It posits that the universe is indifferent to human existence and filled with entities and forces so alien and powerful that merely comprehending them could drive one to madness. As we embark on this exploration of cosmic horrors, we must prepare ourselves for revelations that will challenge our understanding of reality and our place within it. The universe, in its infinite expanse and complexity, holds terrors beyond our wildest nightmares. If you're ready to explore these cosmic horrors, make sure to like this video and subscribe to our channel for more mind-bending content. The void, infinite emptiness of space. In the depths of the cosmos lies a horror so profound, so all-encompassing that it defies our very notions of existence. We speak of the void, the vast empty expanses that dominate our universe. As we peer into the darkness between the stars, we confront a terrifying truth. The overwhelming majority of our cosmos is nothing but empty space. To truly grasp the terror of the void, we must first comprehend its scale. Imagine, for a moment, that you could shrink our entire solar system down to the size of a grain of sand. On this scale, the nearest star to our sun, Proxima Centauri, would still be over 4 kilometers away. Now, expand your mind further. The Milky Way galaxy, home to hundreds of billions of stars, would span a continent. And yet, even at this unimaginable scale, the spaces between galaxies dwarf anything we've considered so far. These cosmic voids, the largest known structures in the universe, can span hundreds of millions of light years. To put this in perspective, if the Milky Way were the size of a coin, the nearest large galaxy, Andromeda, would be about a meter away. But the voids between galaxy clusters, they would stretch for kilometers. But what exactly is a void? In cosmological terms, a void is a vast region of space containing very few or no galaxies. These cosmic deserts make up about 80% of the universe's volume. Let that sink in for a moment. 80% of everything that exists is, essentially, nothing. The largest known void, dubbed the Bouteille's Void or the Great Void, spans an incomprehensible 330 million light-years in diameter. If our Milky Way were placed at the center of this void, we wouldn't have known there were other galaxies in the universe until the 1960s. Our most powerful telescopes would have shown nothing but darkness in every direction. But the terror of the void goes beyond mere emptiness. These vast expanses challenge our understanding of physics and the nature of reality itself. According to our current models of cosmic evolution, matter should be distributed much more evenly throughout the universe. The existence of these enormous voids suggests that there are fundamental aspects of cosmic structure formation that we still don't understand. Moreover, these voids are not truly empty. They're filled with dark energy, the mysterious force driving the accelerating expansion of our universe. As we peer into the void, we're looking at the very fabric of space-time, stretched to its limit by forces we can barely comprehend. The concept of the void taps into some of our deepest existential fears. It confronts us with the vast emptiness that surrounds our tiny island of existence. In the face of such overwhelming nothingness, our very being seems fragile and insignificant. Imagine for a moment being lost in one of these cosmic voids. You're adrift in a sea of darkness so vast that the likelihood of encountering another particle, let alone another living being, approaches zero. The nearest star is millions of light years away, a distance so great that even if you could travel at the speed of light, you would die long before reaching it. This is not mere fantasy, it's a potential reality based on our current understanding of the universe's structure and expansion. The void also challenges our notions of time and causality. In the emptiness between galaxies, with no reference points and no events to mark the passage of time, how would you perceive your own existence? Would time lose all meaning? Would consciousness itself begin to unravel in the face of eternal, unchanging emptiness? But the horror of the void doesn't end there. As our universe continues to expand, driven by the mysterious force of dark energy, these voids are growing larger. In the far distant future, they may come to dominate the cosmos entirely. Imagine a universe where galaxies are so far apart that the light from one can never reach another. Each island of matter would be alone in an infinite sea of darkness, forever cut off from the rest of creation. This scenario, known as the Big Freeze or heat death of the universe, is one possible ultimate fate for our cosmos. As the universe expands, it cools. Eventually, all stars will burn out, all matter will decay, and even black holes will evaporate through Hawking radiation. What's left will be an endless void populated only by the occasional stray particle, eternally drifting through an infinite darkness. Yet even in the face of such cosmic horror, human ingenuity finds ways to probe and understand these voids. Scientists use these empty regions as enormous cosmic laboratories. The absence of matter makes voids ideal for studying dark energy, the mysterious force driving cosmic expansion. By observing how galaxies move at the edges of voids, researchers can measure the strength of dark energy and test theories about the nature of gravity on the largest scales. Voids also serve as cosmic magnifying glasses. As light from distant galaxies passes through a void, it's not disrupted by intervening matter. This allows astronomers to see farther and more clearly, potentially revealing secrets about the early universe and the nature of cosmic structure. Moreover, the study of voids has led to surprising discoveries about the nature of matter distribution in the universe. The cosmic web, the large-scale structure of matter in the cosmos, is shaped as much by these empty regions as by the dense clusters of galaxies. Voids push matter apart, while gravity pulls it together, creating a vast cosmic honeycomb of filaments, walls, and knots of galaxies surrounding enormous bubbles of emptiness. But perhaps the most profound impact of the void is philosophical. As we confront the vast emptiness of the cosmos, we're forced to grapple with questions of meaning and purpose. In a universe dominated by nothingness, what significance can we ascribe to our brief flicker of consciousness? Are we, as physicist Alan Guth suggested, the result of a quantum fluctuation in a vast cosmic void? Yet paradoxically, the void also highlights the preciousness of existence. In a universe overwhelmingly composed of emptiness, the fact that anything exists at all becomes a profound mystery. Our very being, the complexity of life, the richness of human experience, all of these stand in stark contrast to the void that surrounds us. Perhaps then, the true horror of the void is not in its emptiness, but in the mirror it holds up to our own existence. The concept of the void has not only terrified scientists and philosophers, but has also permeated our culture, influencing literature, art, and popular media. In H.P. Lovecraft's cosmic horror stories, the vast emptiness of space often serves as a backdrop for incomprehensible alien terrors. Modern science fiction frequently grapples with the psychological impact of deep space travel, where characters must confront the overwhelming emptiness that surrounds them. In visual art, the void has been a subject of fascination for centuries. From Caspar David Friedrich's Monk by the Sea, which presents a tiny human figure dwarfed by an expansive empty sky, to contemporary installations that create experiences of infinite space, artists have long attempted to capture the sublime terror of nothingness. The void also plays a significant role in various philosophical and religious traditions. In some Eastern philosophies, the concept of emptiness or void, sunyata in Buddhism for example, is seen not as a terrifying absence, but as the fundamental nature of reality, free from the illusions of permanence and self. This presents an interesting counterpoint to the Western cosmic horror perspective, suggesting that embracing the void might be a path to enlightenment rather than a source of existential dread. From a scientific perspective, the study of cosmic voids continues to yield fascinating insights. Recent research has suggested that voids might be more dynamic than previously thought. Some scientists propose that voids could contain tenuous filaments of matter, forming a void web that mirrors the cosmic web on a much larger scale. If confirmed, this would challenge our understanding of structure formation in the universe and potentially provide new clues about the nature of dark matter and dark energy. Moreover, the properties of voids might hold the key to resolving some of the most pressing puzzles in cosmology. For instance, the Hubble tension, a discrepancy between different measurements of the universe's expansion rate, might be explained by our location relative to cosmic voids. If we happen to live in a relatively empty region of space, it could affect our observations of distant galaxies and lead to misleading conclusions about the overall expansion of the universe. The void also plays a crucial role in our understanding of galaxy formation and evolution. Computer simulations have shown that the interplay between voids and the cosmic web is essential for shaping the galaxies we see today. Galaxies in void regions tend to be smaller, bluer, and more actively forming stars than those in denser environments. This cosmic nurture effect demonstrates how the vast emptiness of space directly influences the properties of the matter within it. As we push the boundaries of our observations, we're discovering that even the deepest voids are not entirely empty. Ultra-faint dwarf galaxies and isolated stars have been detected in what were once thought to be completely barren regions of space. These lonely outposts of matter in the cosmic desert raise intriguing questions about how they formed and survived in such isolated environments. The void also presents unique opportunities for future space exploration. While the vast distances involved make interstellar travel challenging, the relative emptiness of space between star systems could actually be advantageous for certain technologies. For instance, solar sails, spacecraft propelled by the pressure of sunlight or laser beams, could potentially achieve higher speeds in the near vacuum of interstellar space than in the relatively cluttered environment of our solar system. However, the void also presents existential risks to our long-term survival as a species. As the universe continues to expand and the voids grow larger, they will eventually make it impossible for us to observe or interact with anything beyond our local group of galaxies. This cosmic isolation could limit our potential for expansion and resource utilization on a truly cosmic scale. Furthermore, the nature of the void forces us to confront the possibility that we might truly be alone in the universe. If life is as rare as the emptiness of space suggests, we may be the only conscious observers in our cosmic neighborhood, bearing the weight of being the universe's sole witnesses to its own existence and eventual fate. As we conclude our exploration of the cosmic void, we're left with a mixture of terror and awe. The void represents the ultimate expression of cosmic horror, an emptiness so vast and absolute that it challenges our very notion of reality. Yet it also embodies the deepest mysteries of our universe, holding clues to the nature of space, time, and existence itself. In the face of such overwhelming emptiness, our human endeavors might seem insignificant, but perhaps it's precisely this contrast that gives meaning to our existence. In a universe dominated by void, we are the anomaly, islands of complexity and consciousness in an ocean of nothingness. Our ability to perceive, understand, and find wonder in the cosmos, even in its most terrifying aspects, is nothing short of miraculous. The void, in all its terrifying emptiness, serves as a cosmic canvas upon which the greatest story of all, that of existence itself, is written. It is the stage upon which galaxies dance, stars live and die, and conscious beings like ourselves emerge to contemplate the nature of reality. In our quest to understand the void, We are really seeking to understand ourselves and our place in this vast, mostly empty universe. As we move forward in our journey through cosmic horrors, the void will remain a constant presence, an inescapable backdrop to all the other terrors we will encounter. It is the ultimate context for our existence, the silent witness to the unfolding drama of the cosmos. In confronting the void, we confront the very essence of what it means to exist in a universe that is, paradoxically, defined as much by what isn't there as by what is. Black holes, cosmic destroyers. In the vast tapestry of cosmic horrors, few phenomena inspire as much terror and awe as black holes. These cosmic destroyers, born from the death throes of massive stars or lurking in the hearts of galaxies, represent the ultimate breakdown of our understanding of physics. They are nature's own cosmic horror story, where the familiar laws of reality crumble and give way to a nightmare realm of extreme gravity. To truly comprehend the terror of black holes, we must first understand their nature. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape its grasp. This creates the eponymous blackness, an area of absolute darkness against the backdrop of space. But this darkness is merely the surface of a far more terrifying reality. The boundary of a black hole, known as the event horizon, marks the point of no return. Once anything crosses this threshold, be it light, matter, or information itself, it can never escape. It's a one-way ticket to oblivion, a journey from which there is no return. The event horizon is not a physical surface, but a point of no return in space-time itself. It's a cosmic point of existential horror, the ultimate prison from which escape is not merely improbable, but fundamentally impossible. As we approach the center of a black hole, we encounter the singularity, a point where the curvature of space-time becomes infinite and the laws of physics as we know them cease to apply. It's a realm where our most fundamental theories of the universe fail, where reality itself seems to unravel. The singularity represents a fundamental limit to our knowledge, a cosmic horror, not just of destruction, but of the unknown. What happens to matter as it approaches the singularity? Does it compress to infinite density? Does it transition to some other state of existence beyond our comprehension? Or does it perhaps emerge in another universe entirely? These questions push at the boundaries of our understanding, hinting at realms of reality beyond our current grasp. The terror of black holes extends far beyond their interior. Their immense gravitational pull warps the very fabric of space-time around them, creating a cosmic maelstrom that can tear apart stars and devour entire solar systems. Imagine a celestial body so massive that it can bend light itself, creating gravitational lenses that distort our view of the universe. Black holes don't just destroy, they fundamentally alter the nature of space and time in their vicinity. One of the most mind-bending aspects of black holes is their effect on time itself. As you approach a black hole, time begins to slow down relative to the outside universe, a phenomenon known as time dilation. This effect becomes more pronounced the closer you get to the event horizon. If you were to watch a clock falling into a black hole, you would see it tick ever more slowly, finally freezing at the event horizon. From the perspective of the falling clock, however, time would proceed normally, while the outside universe would appear to speed up, rushing towards its heat death in the blink of an eye. This time dilation leads to one of the most disturbing thought experiments in astrophysics, the fate of an astronaut falling into a black hole. From the perspective of a distant observer, the unfortunate explorer would appear to slow down as they approach the event horizon, their image growing redder and dimmer, but never quite reaching the horizon itself. They would seem frozen in time at the edge of the black hole, slowly fading from view over millions of years. But for the falling astronaut, the experience would be drastically different and far more terrifying. They would pass the event horizon without noticing anything unusual, but as they continued to fall, they would witness the entire future history of the universe unfold before their eyes in a matter of moments. Stars would live and die, galaxies would collide and disperse, and the universe itself would age towards its heat death, all while the astronaut plummeted ever deeper into the black hole's maw. This scenario, known as the spaghettification process, only gets more horrifying. As the astronaut falls deeper into the black hole, the The difference in gravitational pull between their head and feet would become so extreme that they would be stretched out like cosmic spaghetti, their very atoms torn apart by tidal forces. It's a death of unimaginable agony stretched across the entire lifespan of the universe from the perspective of outside observers. But individual black holes, as terrifying as they are, pale in comparison to their supermassive cousins lurking at the centers of galaxies. Our own Milky Way harbors one such monster, Sagittarius A*, with a mass of about 4 million suns. These galactic leviathans can have event horizons larger than our entire solar system, their gravitational influence shaping the evolution of entire galaxies. The largest known black hole, at the center of the galaxy Ton 618, is truly the stuff of cosmic nightmares. With a mass of 66 billion suns, it's a void so vast it could swallow our entire solar system thousands of times over. The scale of such an object defies comprehension. It's a cosmic horror on a galactic scale. Yet for all their destructive power, black holes are also engines of creation. As matter falls into a black hole, it forms an accretion disk, a swirling maelstrom of superheated gas and dust. This process can trigger the birth of new stars and even influence galaxy formation. The jets of particles sometimes emitted by spinning black holes can stretch for thousands of light years, shaping the intergalactic medium. In a universe of cosmic horrors, black holes remind us that creation and destruction are often two sides of the same coin. The enigma of black holes extends to their very existence. According to quantum mechanics, information cannot be destroyed. Yet black holes seem to erase all information about what falls into them. This apparent contradiction, known as the black hole information paradox, has puzzled physicists for decades. It suggests that either our understanding of quantum mechanics is incomplete, or that black holes are even stranger than we imagine, perhaps preserving information in ways we don't yet understand. This paradox hints at an even more mind-bending possibility, that our entire universe might be a holographic projection from information stored on the event horizons of black holes. This holographic principle suggests that the three-dimensional reality we experience might be an illusion, a projection from a two-dimensional surface at the edge of the universe. It's a concept that blurs the line between physics and philosophy, challenging our most fundamental notions of reality. The study of black holes has also led to one of the most unsettling predictions in modern physics: Hawking radiation. Stephen Hawking proposed that quantum effects near the event horizon could cause black holes to slowly evaporate over time, emitting radiation in the process. While this might seem like a relief, black holes aren't eternal after all. The implications are profoundly disturbing. The final moments of a black hole's evaporation would release an enormous amount of energy, potentially triggering a new Big Bang. Our universe might be littered with the seeds of future universes, each born from the death throes of an evaporating black hole. As if all this wasn't terrifying enough, recent research has proposed even more mind-bending possibilities. Some theories suggest the existence of exotic variants like naked singularities, where the singularity is visible outside the event horizon, traversable wormholes, shortcuts through space-time, potentially linked to black holes, and even white holes, theoretical opposites of black holes that nothing can enter, but from which matter and light can escape. While these concepts remain theoretical, they hint at a universe even stranger and more terrifying than we can imagine. The horror of black holes extends beyond their physical properties to the existential dread they inspire. They represent regions of the universe that are fundamentally unknowable, where the laws of physics break down and our ability to predict and understand fails utterly. In the face of such cosmic monsters, our existence seems fragile and insignificant. We are like ants living on the edge of an endless abyss, our entire world subject to forces we can barely comprehend, let alone control. Yet in true human fashion, we continue to study and probe these cosmic destroyers. Advanced gravitational wave detectors like LIGO have allowed us to hear the space-time ripples caused by colliding black holes, opening a new era of multi-messenger astronomy. Future space-based observatories promise to give us our first direct images of black hole event horizons, peering into the heart of these cosmic monsters. As we push the boundaries of our knowledge, we must confront the possibility that black holes are not just destroyers, but also creators of new physics, new universes, and new ways of understanding reality itself. They force us to grapple with the limits of our knowledge and the vastness of what remains unknown. In contemplating black holes, we confront the ultimate cosmic horror, not just of destruction on an unimaginable scale, but of the breakdown of reality itself. They remind us that the universe is not just stranger than we imagine, but stranger than we can imagine. As we peer into these cosmic abysses, we must wonder, are they looking back? And if so, what unfathomable truths might they reveal about the nature of existence itself? Dark matter, the invisible threat. In the pantheon of cosmic horrors, few concepts are as unsettling as dark matter. It's a specter that haunts the cosmos, an invisible presence that permeates every corner of the universe, including our own world. Unlike the void with its terrifying emptiness, or black holes with their reality-warping gravity, dark matter presents a different kind of horror, the terror of the unseen, the unknown that surrounds us at every moment. To understand the horror of dark matter, we must first grapple with its nature, or rather, our profound lack of understanding of its nature. Dark matter is, as its name suggests, dark. It doesn't interact with light or any other form of electromagnetic radiation. We cannot see it, touch it, or detect it with any of our most advanced scientific instruments, and yet we know it's there. Its presence revealed only through its gravitational effects on visible matter. The first inklings of dark matter's existence came in the 1930s, when astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving much faster than they should be based on their visible mass. It was as if some unseen hand was exerting additional gravitational pull, keeping the cluster from flying apart. This discrepancy between the observed mass and the mass needed to explain the motion of celestial bodies has been observed at all scales in the universe, from individual galaxies to the largest structures we can see. The implications of these observations are staggering. According to our best estimates, dark matter makes up about 85% of all matter in the universe, and about 27% of the universe's total mass energy content. In other words, the vast majority of the matter in our universe is completely invisible and undetectable to us. We are, in a very real sense, blind to most of the universe's contents. This realization strikes at the heart of our cosmic understanding. For centuries, we've prided ourselves on our ability to observe and comprehend the universe. We've built ever more powerful telescopes, probed the depths of the atom, and unraveled the genetic code of life. And yet, here is a substance that makes up the majority of matter in the universe, and we can't even detect it directly. It's a humbling reminder of the limits of our knowledge and perception. But the horror of dark matter goes beyond mere invisibility. Its presence shapes the very structure of the cosmos. The galaxies we see, the cosmic web that spans the universe, the very distribution of matter on the largest scales, all of these are thought to be the result of dark matter's gravitational influence. Our visible universe is but a pale reflection of the dark matter scaffolding that underlies it. Consider the implications of this: the ground beneath your feet, the air you breathe, the very atoms that make up your body. All of these are part of a minority component of the universe. We are, in a sense, living in the shallows of a vast, dark ocean that we cannot perceive. Every moment of every day, dark matter particles are likely passing through your body unseen and unfelt. You are immersed in a sea of invisible matter, oblivious to its ebb and flow. The nature of dark matter particles themselves is a source of profound unease. Despite decades of searching, we have yet to directly detect a dark matter particle. We know they must be fundamentally different from the particles that make up ordinary matter. They don't interact via the electromagnetic force, which means they can pass through normal matter as if it weren't there. Some theories suggest they might be able to interact with themselves or with normal matter via the weak nuclear force, but even this is uncertain. One leading candidate for dark matter is a hypothetical particle called a WIMP, or weakly interacting massive particle. These particles, if they exist, would be relatively heavy, but interact only very weakly with ordinary matter. The idea that massive particles could be constantly streaming through us, undetected and unstoppable, is deeply unsettling. It challenges our notion of the solidity and separateness of objects in the world around us. Other candidates for dark matter are even stranger. Axions, for instance, are hypothetical particles that could switch between matter and antimatter states. Some theories propose that dark matter could be made up of primordial black holes, relics from the early universe too small to detect directly, but massive enough to exert significant gravitational influence. There are even suggestions that dark matter could be a manifestation of extra dimensions of space-time, invisible to us but exerting their influence on the visible universe. The search for dark matter has led to the construction of some of the most sensitive detectors ever built. Deep underground, shielded from cosmic rays and other sources of interference, these devices wait patiently for the faintest signal of a dark matter particle interaction. So far, they have detected nothing. The silence of these detectors is itself a kind of cosmic horror, a reminder of how elusive and alien dark matter is to our normal experience of the universe. But perhaps the most unsettling aspect of dark matter is its implications for the fate of the universe. The gravitational pull of dark matter plays a crucial role in cosmic structure formation and evolution. It's the invisible hand that has guided the formation of galaxies and galaxy clusters. As we look to the future of the cosmos, dark matter will play a decisive role. Will its gravitational influence eventually halt the expansion of the universe, leading to a big crunch? Or will it be overcome by the even more mysterious dark energy, leading to an ever-accelerating expansion and the heat death of the universe? The influence of dark matter extends to our own galactic neighborhood. The Milky Way is thought to be surrounded by a vast halo of dark matter, extending far beyond the visible disk of the galaxy. This halo interacts gravitationally with smaller galaxies, potentially drawing them in and tearing them apart. Our galaxy's two largest satellite galaxies, the Large and Small Magellanic Clouds, are currently being disrupted by the Milky Way's dark matter halo. In the night sky, we can see the streams of stars torn from these galaxies, visible evidence of dark matter's destructive power. Even more unsettling is the possibility that dark matter could form structures on smaller scales. Some theories predict the existence of dark matter clumps or halos within our own solar system. These invisible concentrations of mass could potentially influence the orbits of planets and comets, introducing a subtle but persistent chaos into what we thought was a well-ordered system. The concept of dark matter also raises profound questions about the nature of life and intelligence in the universe. If most of the matter in the universe is dark matter, could there be forms of life based on dark matter particles? Such life would be completely invisible and undetectable to us, potentially coexisting with us in the same space, but in a parallel dark matter world. The idea that we could be sharing our planet, our solar system, our galaxy with invisible dark matter entities is both fascinating and deeply unsettling. This concept has been explored in science fiction, with some stories positing dark matter intelligences vastly older and more advanced than our own. In these narratives, humanity's ignorance of dark matter often leads to cosmic horror scenarios where we inadvertently disturb or anger these ancient invisible entities. While purely speculative, such ideas highlight the potential for dark matter to completely upend our understanding of life and intelligence in the cosmos. The study of dark matter also intersects with other areas of cutting-edge physics in ways that amplify its cosmic horror potential. For instance, some theories link dark matter to the concept of quantum entanglement, suggesting that dark matter particles could be entangled across vast distances. This could potentially allow for faster-than-light communication or even causality violation, concepts that challenge our fundamental understanding of how the universe works. Another unsettling possibility is the idea of mirror matter, a hypothetical form of dark matter that could form parallel structures to ordinary matter, including mirror atoms, mirror chemistry, and even mirror life. This concept suggests a shadow universe overlapping with our own, invisible and intangible, yet profoundly influencing the evolution of the cosmos. The search for dark matter has also led scientists to consider increasingly exotic possibilities. Some researchers have proposed that dark matter could be a manifestation of quantum vacuum fluctuations, essentially meaning that the nothing of empty space could be the source of most of the universe's matter. Others have suggested that dark matter could be a sign that our understanding of gravity itself is fundamentally flawed, leading to modified theories of gravity that do away with dark matter entirely, but introduce other, equally unsettling implications. As we delve deeper into the mystery of dark matter, we are forced to confront the possibility that our understanding of the universe is profoundly incomplete. The invisible influence of dark matter serves as a constant reminder of our cosmic ignorance. It suggests that the universe is far stranger and more complex than we can currently comprehend, with layers of reality beyond our perception. This realization can induce a kind of existential vertigo. We are not just tiny specks in a vast cosmos. We are tiny specks of visible matter in a universe dominated by an invisible, intangible substance. Our existence is predicated on and shaped by forces we cannot see or fully understand. Every moment we are surrounded by and permeated with a substance that defies our attempts at detection or comprehension. Yet in true human fashion, we continue to probe and question. The search for dark matter pushes the boundaries of our technology and our theories. It forces us to consider new possibilities and challenge our most fundamental assumptions about the nature of reality. In this sense, dark matter is not just a source of cosmic horror, but also a driver of human ingenuity and scientific progress. As we conclude our exploration of dark matter, we are left with more questions than answers. The invisible threat of dark matter looms over our understanding of the cosmos, a constant reminder of the vast unknowns that surround us. It challenges us to expand our perception, to seek out the unseen and the unknown. In facing the cosmic horror of dark matter, we confront the limits of our knowledge and the boundless mystery of the universe. The terror of dark matter lies not in what we know, but in what we don't know, and perhaps can never know. It's a cosmic horror that whispers of greater mysteries, of layers of reality beyond our perception, of a universe far more vast and strange than we can imagine. As we peer into the darkness searching for signs of this invisible matter, we must wonder what other cosmic horrors might be lurking just beyond the reach of our understanding. Gamma-ray bursts, interstellar death beams. In the vast theater of cosmic horrors, few phenomena are as terrifying and awe-inspiring as gamma-ray bursts, or GRBs. These colossal explosions, the most energetic events in the universe since the Big Bang, serve as nature's own doomsday devices. They are cosmic dragons, capable of breathing destruction across interstellar distances, sterilizing entire galaxies, and potentially ending life on a cosmic scale. To truly grasp the horror of gamma-ray bursts, we must first comprehend their unimaginable power. A typical gamma-ray burst releases as much energy in a few seconds as our sun will produce in its entire 10 billion-year lifetime. This is equivalent to converting the entire mass of a star as big as our sun completely into energy. The brightness of a GRB can temporarily outshine the rest of the visible universe combined. It's as if the cosmos itself is screaming in agony, emitting a flash of lethal radiation that can be detected across billions of light years. The origin of these cosmic catastrophes lies in the death throes of massive stars or the collision of ultra-dense stellar remnants. When a star much more massive than our sun exhausts its nuclear fuel, its core collapses under its own gravity, forming a black hole. The outer layers of the star, falling inward at nearly the speed of light, are violently ejected along the star's axis of rotation, creating two narrow, oppositely directed jets of plasma and radiation. If one of these jets happens to be pointed at Earth, we detect it as a long-duration gamma-ray burst. Alternatively, when two neutron stars or a neutron star and a black hole collide, they can produce a short-duration gamma-ray burst. These cosmic train wrecks, occurring in a matter of milliseconds, release gravitational waves that ripple the very fabric of space-time, along with a fireball of deadly radiation. The true terror of gamma-ray bursts lies not just in their power, but in their unpredictability and potential for destruction. Unlike many cosmic phenomena that unfold over millions or billions of years, GRBs strike without warning. One moment, a star system could be teeming with life. The next, it could be bathed in lethal radiation, sterilizing entire planets in an instant. Consider the fate of a planet caught in the path of a gamma-ray burst. The initial flash of gamma rays would destroy the ozone layer, leaving the planet's surface exposed to deadly ultraviolet radiation from its parent star. The gamma rays would also trigger complex chemical reactions in the atmosphere, creating smog-like conditions and potentially causing acid rain. The following X-ray and ultraviolet radiation would further irradiate the planet's surface. Any life fortunate enough to survive this initial onslaught would then face years of darkness and cold as nitric oxide generated in the atmosphere would block out sunlight, potentially triggering a cosmic winter. There's evidence to suggest that Earth itself may have been struck by a gamma-ray burst in the past. Some scientists propose that the Ordovician-Silurian extinction event, which wiped out about 85% of marine species 450 million years ago, could have been caused by a nearby GRB. The thought that life on our planet could have been nearly extinguished by a burst of radiation from thousands of light years away is a chilling reminder of our cosmic vulnerability. But the horror of gamma-ray bursts extends far beyond their potential to end life on a single planet. Their effects can be felt across interstellar and even intergalactic distances. A sufficiently powerful GRB could potentially sterilize a significant portion of a galaxy, wiping out countless worlds in a single flash. It's a sobering thought that entire civilizations, with all their hopes, dreams, and achievements, could be snuffed out in an instant by a cosmic accident they never saw coming. The discovery of gamma-ray bursts itself reads like a cosmic horror story. They were first detected in the 1960s by American military satellites designed to monitor for nuclear tests. For years, their origin remained a complete mystery, fueling speculation about everything from alien civilizations to tears in the fabric of space-time. It wasn't until the 1990s that astronomers began to understand their true nature and cosmic origins. Even now, with our advanced understanding, gamma-ray bursts continue to surprise and terrify us. In 2022, astronomers detected GRB 221009A, nicknamed the Boat, brightest of all time. This monster explosion was so powerful that it temporarily blinded most gamma-ray instruments in space, overloaded the detectors on several spacecraft, and even affected Earth's ionosphere. The burst originated from a distant galaxy about 2.4 billion light-years away, and its light had been traveling toward us since before multicellular life evolved on Earth. If this burst had occurred in our own galaxy, even at a distance of tens of thousands of light-years, it could have triggered a mass extinction event on Earth. The existence of such phenomenally destructive events forces us to confront uncomfortable questions about the nature of life in the universe. Could gamma-ray bursts be a solution to the Fermi paradox, explaining why we haven't detected signs of alien civilizations? Perhaps intelligent life is routinely wiped out by these cosmic death beams before it has a chance to spread beyond its home planet. Or perhaps the threat of GRBs forces any sufficiently advanced civilization to abandon their home galaxies, seeking refuge in the vast, relatively empty spaces between galaxies. Moreover, the study of gamma-ray bursts intersects with other areas of extreme physics in ways that amplify their cosmic horror potential. For instance, the jets produced by GRBs are among the fastest-moving macroscopic objects in the universe, approaching the speed of light so closely that the effects of special relativity become pronounced. Time dilation and length contraction, usually the stuff of thought experiments, become real and relevant in understanding these cosmic beacons. The environments that produce gamma-ray bursts are so extreme that they allow us to probe the laws of physics in ways that would be impossible in any earthly laboratory. The hearts of GRBs may be home to exotic states of matter, such as quark-gluon plasmas, where the fundamental constituents of atomic nuclei float freely in a soup of unimaginable temperature and density. Some theories even suggest that the conditions in a GRB might be extreme enough to create microscopic black holes or other exotic phenomena. Gamma-ray bursts also force us to confront the vast scales of the universe in both space and time. The fact that we can detect these explosions from billions of light-years away is a testament to their incredible power. But it also means that every GRB we detect is a message from the distant past. We are seeing these stars die as they were billions of years ago, their light only now reaching our telescopes. It's a reminder of the vast gulf of time and space that separates us from much of the universe, and of how much of cosmic history plays out on scales far beyond human comprehension. The study of gamma-ray bursts has also led to surprising connections with other cosmic phenomena. For instance, short-duration GRBs are now known to be associated with gravitational wave events from neutron star mergers. This realization has opened up the era of multi-messenger astronomy, where we can observe cosmic cataclysms through multiple channels: electromagnetic radiation, gravitational waves, and potentially even neutrinos. Each new way of observing these events reveals new layers of their terrifying nature. Perhaps one of the most unsettling aspects of gamma-ray bursts is how they challenge our notions of cosmic order and predictability. In a universe that often seems to operate on grand, slow timescales, GRBs are reminders of the violence and chaos that lurk beneath the surface. They are cosmic wildcards, capable of rewriting the fate of entire star systems or even galaxies in a matter of seconds. In the face of such phenomena, our own existence seems incredibly fragile and fortuitous. Yet, as with many cosmic horrors, gamma-ray bursts are not without their paradoxes. The same processes that make them so destructive also contribute to the chemical enrichment of the universe. The heavy elements forged in the hearts of massive stars and scattered by GRBs are essential for the formation of planets and the emergence of life as we know it. In a sense, we owe our very existence to the same cosmic processes that could so easily destroy us. As we conclude our exploration of gamma-ray bursts, we are left with a mix of terror and wonder. These cosmic death beams represent both the incredible violence of the universe and its capacity for renewal and creation. They are reminders of our cosmic vulnerability, of the thin line that separates existence from oblivion on a galactic scale. Yet, they are also windows into the most extreme physics in the universe, challenging our understanding and pushing the boundaries of our knowledge. In the face of such overwhelming cosmic forces, our existence seems both miraculous and precarious. We are the products of stars, living in the shadow of their potential to destroy us. Every moment of peace we experience is a respite in a universe capable of unimaginable violence. As we peer into the cosmos, searching for signs of these titanic explosions, we must wonder, how long until our luck runs out? How long until our corner of the galaxy is caught in the crosshairs of one of these interstellar death beams? The threat of gamma-ray bursts serves as a cosmic memento mori, a reminder of the fragility of life in the face of universal forces. It challenges us to appreciate the cosmic miracle of our existence, while also pushing us to understand and perhaps one day mitigate these threats. As we continue our journey through the cosmic horrors of the universe, the specter of gamma-ray bursts will remain, a stark reminder of the awesome and terrible power that shapes our cosmos. Rogue planets, wanderers in the dark. In the vast, cold expanse of interstellar space, far from the warming rays of any star, drift the cosmic nomads known as rogue planets. These celestial bodies, ejected from their parent solar systems or formed in isolation, represent a unique form of cosmic horror. They are worlds without suns, drifting through the eternal night of deep space, their surfaces locked in perpetual darkness and unimaginable cold. To truly grasp the terror of rogue planets, we must first understand their nature. Unlike the planets we're familiar with, which orbit stars in relatively stable patterns, rogue planets have been cast adrift in the cosmos. Some may have been violently ejected from their original solar systems due to gravitational interactions with other planets or passing stars. Others may have formed in isolation from collapsing clouds of gas and dust, never experiencing the embrace of a parent star. The number of these cosmic wanderers is staggering. Astronomers estimate that there could be billions of rogue planets in our Milky Way galaxy alone, potentially outnumbering stars by a factor of 2 or more. This means that the space between stars, far from being empty, is populated by countless dark worlds, silently drifting through the void. The very existence of rogue planets challenges our understanding of planetary formation and evolution. For decades, we've thought of planets as the children of stars, born from the swirling disks of gas and dust that surround young suns. But rogue planets suggest a universe where worlds can form and exist independently of stars, expanding our notion of what constitutes a planet. Imagine the surface of one of these wandering worlds. Without a sun to provide light and heat, a rogue planet would be a place of perpetual darkness and extreme cold. Surface temperatures could plummet to near absolute zero, turning atmospheres into frozen shells and oceans into vast slabs of exotic ice. Any geography would be sculpted not by wind and rain, but by the slow ballet of tidal forces from any moons the planet might possess. Yet despite these harsh conditions, some scientists speculate that rogue planets could potentially harbor life. Beneath their frozen surfaces, these worlds might contain oceans of liquid water, kept warm by internal heat generated from radioactive decay or tidal heating. In these lightless seas, life might evolve around hydrothermal vents, much like the deep-sea ecosystems we find on Earth. The thought of alien life evolving in perpetual darkness, never knowing the light of a sun, is both fascinating and deeply unsettling. The horror of rogue planets extends beyond their inhospitable surfaces. These worlds serve as a stark reminder of the impermanence of cosmic systems we often think of as stable. Our own planet Earth, with its apparently fixed orbit around the Sun, could theoretically be ejected from the solar system under the right circumstances. The thought that our entire world could be cast into the freezing darkness of interstellar space is a chilling reminder of our cosmic vulnerability. Moreover, rogue planets challenge our notions of what constitutes a habitable world. For centuries, we've equated habitability with a planet's ability to sustain liquid water on its surface, typically within a certain distance from its parent star. But rogue planets suggest the possibility of subsurface habitable zones that could extend far beyond the traditional boundaries of a star system. This expands the potential abodes for life in the universe, but also makes the search for such life far more challenging. The discovery and study of rogue planets push the boundaries of our observational capabilities. These dark worlds don't emit light of their own and don't reflect light from a nearby star, making them incredibly difficult to detect. Astronomers have had to develop ingenious methods to find them, including gravitational microlensing, where a rogue planet briefly amplifies the light from a background star as it passes in front of it. One of the most unsettling aspects of rogue planets is their potential to interact with established solar systems. A rogue planet passing through our solar system could gravitationally disrupt the orbits of our planets, potentially ejecting smaller worlds or sending comets and asteroids hurtling towards the inner planets. While such an event is extremely unlikely in any given time frame, the sheer number of rogue planets in the galaxy means that such cosmic close encounters are virtually inevitable over long enough timescales. The concept of rogue planets also intersects with other areas of astronomy in ways that amplify their cosmic horror potential. For instance, some theories suggest that dark matter, the mysterious substance that makes up most of the matter in the universe, could form ultra-cold and ultra-dense planets. These dark matter planets would be even more elusive than normal rogue planets, detectable only through their gravitational effects. Another terrifying possibility is the existence of rogue planets that were once inhabited. Imagine an advanced civilization living on a planet orbiting a stable star, suddenly faced with a cosmic cataclysm that ejects their entire world into interstellar space. Would they have time to prepare? Could they survive the transition to a sunless existence? The idea of ghost worlds drifting through space, perhaps carrying the frozen remains of extinct civilizations, is a chilling one. Rogue planets also force us to confront the vast timescales of cosmic evolution. A planet ejected from its solar system could drift through interstellar space for billions of years. Over such immense periods, it might be captured by another star system, plunging its potentially evolved ecosystems into a new environment. Or it might eventually spiral into the galactic core, to be torn apart by the supermassive black hole lurking there. The life cycle of a rogue planet plays out on timescales far beyond human comprehension. The study of rogue planets has led to some surprising discoveries and theories. For instance, some scientists have proposed that rogue planets could serve as interstellar stepping stones, allowing life to spread between star systems without the need for directed panspermia. A planet ejected from one solar system could, in theory, be captured by another, potentially bringing with it microbial stowaways. This raises the unsettling possibility that life on Earth could have originated on a rogue world that was later captured by our Sun. Another intriguing and somewhat terrifying possibility is the existence of rogue moons. If a gas giant planet were ejected from its solar system, it could carry with it a system of moons. These moons, warmed by tidal heating from their parent planet, could potentially maintain subsurface oceans and even life, creating oases of habitability drifting through the interstellar void. The concept of rogue planets has also captured the imagination of science fiction writers, who have explored the potential horrors and wonders of these wandering worlds. Some stories depict rogue planets as arks, carrying the last survivors of dead civilizations through space. Others imagine them as prisons, where the most dangerous criminals in the galaxy are exiled to drift eternally in the cosmic void. The idea of a world without a sun taps into primal human fears of darkness and isolation, making rogue planets a fertile ground for cosmic horror narratives. As we contemplate rogue planets, we're forced to confront the vastness and loneliness of cosmic existence. These wandering worlds serve as a reminder that the universe is largely cold, dark, and empty. They challenge our notions of what constitutes a planet, what environments could potentially harbor life, and how stable we can consider our own cosmic environment to be. The existence of rogue planets also raises profound philosophical questions. If life can exist on a sunless world, drifting through the void between stars, how does that change our understanding of our place in the cosmos? What would be the psychology of beings evolved to live in eternal darkness, never knowing the light of a sun? How would they conceive of the universe without the daily cycle of light and dark that has shaped our own evolution and mythologies? As we conclude our exploration of rogue planets, we're left with a mixture of terror and wonder. These cosmic wanderers represent both the incredible hostility of the universe and its potential for surprise and adaptation. They are reminders of the precariousness of our own existence, of how much our lives depend on the stable orbit and warming rays of our sun. Yet they also expand our understanding of the potential abodes for life in the universe, challenging us to think beyond our sun-centric notions of habitability. In the face of such cosmic nomads, our own planet seems both incredibly fortunate and terrifyingly vulnerable. We are, in a sense, all inhabitants of a spaceship Earth, hurtling through the cosmos. The existence of rogue planets reminds us that our journey is not guaranteed to be stable or eternal. As we peer into the darkness between the stars, searching for these elusive worlds, we must wonder how many of them are out there, and could our own planet one day join their lonely wanderings? The specter of rogue planets will continue to haunt our exploration of the cosmos. They represent a form of cosmic horror that is both subtle and profound, not the explosive violence of supernovae or the reality-warping power of black holes, but the slow, cold terror of eternal drift and isolation. Neutron stars. In the grand tapestry of cosmic horrors, few objects embody the extremes of nature quite like neutron stars. These stellar corpses, born from the cataclysmic deaths of massive stars, represent a state of matter so dense, so extreme, that they blur the line between the macro and micro scales of the universe. They are cosmic zombies, dead stars that continue to exert a powerful influence on their surroundings, their very existence a testament to the unimaginable forces at play in the cosmos. To truly grasp the terror of neutron stars, we must first comprehend their genesis and nature. When a star much more massive than our Sun exhausts its nuclear fuel, it explodes in a supernova, one of the most energetic events in the universe. But what's left behind can be even more terrifying than the explosion itself. If the stellar core surviving the supernova is between about 1.4 and 3 solar masses, it collapses under its own gravity, crushing protons and electrons together to form neutrons. The result is a neutron star, an object with the mass of a sun crammed into a sphere only about 20 kilometers in diameter. The density of a neutron star defies comprehension. A single teaspoon of neutron star material would weigh as much as all the humans on Earth, about 4 billion tons. The gravity at the surface of a neutron star is so intense that it warps space-time significantly, causing light to bend and creating gravitational time dilation effects. If you were to somehow stand on the surface of a neutron star, you would be crushed to a thin film less than 1 atom thick. The escape velocity at the surface is about half the speed of light. Any slower, and you'd fall back to the star, unable to escape its gravitational clutches. But the horror of neutron stars goes far beyond their incomprehensible density. These stellar remnants are cosmic beacons of death, constantly broadcasting their presence across the galaxy. Many neutron stars rotate rapidly, emitting beams of electromagnetic radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse, giving rise to the phenomenon we observe as pulsars. Some pulsars rotate hundreds of times per second, their unimaginable mass whirling at speeds that strain our understanding of physics. The magnetic fields of neutron stars are equally terrifying. The strongest magnetic fields observed in the universe belong to a class of neutron stars called magnetars. These fields are so powerful, quadrillions of times stronger than Earth's magnetic field, that they could strip the information from a credit card at a distance halfway to the moon. Near a magnetar, atoms themselves are distorted into cigar shapes, and chemistry as we know it becomes impossible. The magnetic field is so intense that it generates massive amounts of energy, causing the neutron star's crust to crack and shift in devastating starquakes. These starquakes can release immense bursts of energy. In 2004, a giant flare from the magnetar SGR 1806-20 released more energy in a tenth of a second than our sun emits in 150,000 years. This burst of radiation from a source 50,000 light-years away was so powerful that it saturated the detectors of every spacecraft watching the sky and briefly ionized Earth's upper atmosphere. If such an event were to occur within a few thousand light-years of Earth, it could potentially trigger a mass extinction event. The extreme nature of neutron stars makes them cosmic laboratories for testing the laws of physics under conditions impossible to recreate on Earth. The interiors of neutron stars are thought to contain exotic states of matter, including superfluids and superconductors made of neutrons. Some theories suggest that the core of a neutron star might contain free quarks, the subatomic particles that make up protons and neutrons, creating a state of matter called quark-gluon plasma that hasn't existed since moments after the Big Bang. But perhaps the most unsettling aspect of neutron stars is how they challenge our notions of life and death on a stellar scale. These are the corpses of once mighty stars, and yet they continue to influence their surroundings in profound ways. They can strip material from companion stars, accumulate matter until they collapse into black holes, or collide with other neutron stars in cataclysmic events that shake the very fabric of space-time and create most of the heavy elements in the universe. The collision of two neutron stars is a cosmic horror show of unimaginable proportions. In August 2017, astronomers detected gravitational waves from such a collision, an event named GW 170817. In the final seconds before the collision, these city-sized objects were orbiting each other at about 30% of the speed of light. The merger released a burst of gamma rays and triggered the creation of heavy elements like gold and platinum, scattering them into space in a kilonova explosion. It's a sobering thought that the gold in your jewelry was likely forged in such a violent cosmic forge. Neutron stars also force us to confront the limits of our understanding of physics. At the density of a neutron star, quantum effects become important on a macroscopic scale. The entire star can be thought of as a single, massive atomic nucleus. The physics governing the behavior of matter under such extreme conditions is still not fully understood, and neutron stars continue to surprise us with their properties and behavior. One of the most perplexing aspects of neutron stars is their perfect sphericity. Despite rotating at incredible speeds, neutron stars are the most perfect spheres known in the universe. Any mountain on a neutron star would be at most about 5 millimeters high. This perfection is a result of the star's enormous gravity, which smooths out any irregularities. It's as if the cosmos is mocking us with the mathematical perfection of these dead stars. The study of neutron stars intersects with other areas of astrophysics in ways that amplify their cosmic horror potential. For instance, neutron stars in binary systems with black holes create some of the most extreme environments known in the universe. As the black hole strips material from the neutron star, it creates a disk of plasma hot enough to emit X-rays. Eventually, the black hole may completely consume the neutron star in an event that would release enormous amounts of energy and gravitational waves. Another terrifying possibility is the existence of quark stars or strange stars. These hypothetical objects would be even denser than neutron stars composed entirely of quark matter. If they exist, strange stars would represent an entirely new state of matter, one that could potentially convert any normal matter it contacts into more strange matter. Some scientists have even speculated about the possibility of strangelet contamination, where a small piece of strange matter could potentially convert an entire planet into strange matter. While this scenario is considered highly unlikely, it represents the kind of existential threat that neutron stars and their even more exotic cousins pose to our understanding of the universe. The extreme properties of neutron stars also make them potential candidates for advanced civilizations to exploit. Their intense gravity and magnetic fields could be harnessed for energy or propulsion on a scale far beyond anything we can currently achieve. Some scientists have even proposed using pulsars as natural beacons for interstellar navigation. The idea that these stellar corpses could become the foundation for cosmic engineering projects adds another layer of cosmic horror to their existence. As we contemplate neutron stars, we're forced to confront the violent and extreme nature of the universe. These objects represent a state of matter so far removed from our everyday experience that they seem to belong more to the realm of science fiction than reality. And yet, our galaxy is littered with these stellar zombies, their lighthouse-like beams sweeping through space, their intense gravity and magnetic fields shaping their surroundings. The existence of neutron stars also raises profound questions about the nature of matter and the limits of physical law. What happens to matter when it's crushed beyond the limits of atomic structure? How does quantum physics behave when scaled up to stellar masses? Can life exist in any form near these cosmic beacons of death? These questions push at the boundaries of our knowledge, hinting at realms of physics yet to be understood. Moreover, neutron stars serve as a grim reminder of the life cycle of stars and the ultimate fate that awaits many of the bright points of light we see in the night sky. They are stellar memento mori, reminding us that even the most massive and brightest stars are doomed to die, leaving behind these crushed remnants as their headstones. As we conclude our exploration of neutron stars, we're left with a mixture of awe and terror. These cosmic objects represent both the incredible violence of the universe and its capacity for creating conditions so extreme they can barely be imagined. They are reminders of how much of the universe exists in states utterly alien and hostile to life as we know it. Yet paradoxically, the same processes that create neutron stars also seed the cosmos with the heavy elements necessary for life. In the face of such extreme cosmic phenomena, our existence seems both miraculous and precarious. We live in a universe where stars can collapse into objects so dense that a teaspoon of their material would outweigh a mountain, where magnetic fields can be strong enough to distort the very atoms that make up matter, where stellar corpses can spin hundreds of times a second without flying apart. The neutron stars scattered throughout our galaxy serve as cosmic lighthouses, not guiding us to safe harbor, but warning us of the unimaginable forces and conditions that exist in the universe. As we continue to study these extreme objects, we push the boundaries of our understanding of physics and the nature of matter itself. In the crushed remnants of stellar death, we find a cosmic horror that challenges our comprehension and reminds us of the awesome and terrifying nature of the universe we inhabit. Supernovae, stellar explosions of unimaginable power. In the grand theater of cosmic horrors, few events can match the sheer destructive power and awe-inspiring spectacle of a supernova. These cataclysmic explosions, marking the violent deaths of stars, release energy on a scale that defies human comprehension. They are nature's most powerful explosions, cosmic harbingers of destruction and creation, capable of outshining entire galaxies and seeding the universe with the building blocks of life. To truly grasp the terror of supernovae, we must first understand their genesis and nature. A supernova occurs when a star, having exhausted its nuclear fuel, can no longer support itself against its own gravity. For massive stars, this leads to a core collapse supernova. The star's core, no longer held up by the outward pressure of fusion reactions, collapses in on itself in a matter of seconds. The outer layers of the star, suddenly unsupported, fall inward at speeds approaching a quarter of the speed of light. When these infalling layers hit the collapsed core, they bounce back with tremendous force, creating a shockwave that rips through the star. This shockwave, coupled with a flood of neutrinos produced in the core, tears the star apart in an explosion of unimaginable violence. In a single second, a supernova can release more energy than our sun will produce in its entire 10 billion year lifetime. The scale of a supernova explosion is truly cosmic. At its peak, a single supernova can outshine an entire galaxy of hundreds of billions of stars. If a supernova were to occur at the center of our Milky Way galaxy, some 25,000 light-years away, it would appear as bright as the full moon in our sky, visible even in broad daylight. The explosion would release a flood of high-energy particles and radiation that could potentially disrupt Earth's ozone layer, leading to increased ultraviolet exposure at the surface. But the horror of supernovae extends far beyond their immediate destructive power. These cosmic explosions are factories of both creation and destruction on a galactic scale. The intense heat and pressure of a supernova create conditions that can synthesize heavy elements, forging them in the fires of stellar death. Most of the elements heavier than iron in the universe, including the gold in your jewelry and the calcium in your bones, were created in the hearts of dying stars and scattered across space by supernovae. This dual nature of supernova, bringers of both death and the seeds of new life, embodies a cosmic horror that challenges our understanding of existence itself. We are, in a very real sense, the children of long-dead stars. Our very bodies are composed of atoms forged in stellar furnaces and distributed by these cosmic explosions. As Carl Sagan famously said, we are made of star stuff. But that star stuff was violently torn apart and scattered across the cosmos in explosions of unimaginable power. The effects of a supernova can be felt across vast distances of space. The shockwave from the explosion creates an expanding bubble of hot gas and debris known as a supernova remnant. These remnants can persist for thousands of years, shaping the interstellar medium and triggering the formation of new stars. The Crab Nebula, one of the most famous objects in the night sky, is the remnant of a supernova that was observed by Chinese astronomers in 1054 AD. Nearly 1,000 years later, it continues to expand at speeds of about 1,500 kilometers per second. But supernovae are not just distant spectacles. There's evidence that they have had a direct impact on life on Earth. Some scientists believe that a nearby supernova may have contributed to a minor mass extinction event about 2.6 million years ago. Traces of radioactive iron-60, which can only be produced in significant quantities by supernovae, have been found in deep-sea deposits dating from this period. It's a chilling reminder that events happening light-years away can have profound effects on our planet. The study of supernovae has led to some of the most startling discoveries in modern astronomy. In the late 1990s, observations of distant supernovae led to the realization that the expansion of the universe is accelerating, a discovery that earned the 2011 Nobel Prize in Physics. This acceleration, attributed to the mysterious force known as dark energy, implies a future for our universe that is perhaps the ultimate cosmic horror, an eternity of ever-increasing emptiness and cold. Supernovae also serve as cosmic distance markers, allowing astronomers to measure the vast scales of the universe. The consistency of certain types of supernovae allows them to be used as standard candles to determine the distances to far-off galaxies. It's through the violent deaths of stars that we've been able to map the structure and expansion of the cosmos. But perhaps the most unsettling aspect of supernovae is their unpredictability. Unlike many cosmic phenomena that unfold over millions or billions of years, a supernova can occur with little warning. A star that has shone steadily for millions of years can, in its final moments, brighten to outshine its entire galaxy before fading away. This unpredictability serves as a stark reminder of the volatile nature of the cosmos. In our own galactic neighborhood, several stars are prime candidates for going supernova in the, astronomically near future. Betelgeuse, a red supergiant in the constellation Orion, could explode at any time in the next 100,000 years, a blink of an eye in cosmic terms. When it does, it will be visible from Earth even in broad daylight for weeks. While it's too far away to pose a direct threat to Earth, it serves as a constant reminder of the cosmic time bombs ticking away in our night sky. Even more unsettling is the possibility of a supernova occurring much closer to Earth. The star system IK Pegasi, located only 150 light-years away, contains a white dwarf that is accreting matter from its companion star. If the white dwarf reaches a critical mass, it could trigger a Type Ia supernova, an explosion that would have severe consequences for life on Earth. While the chance of this happening in the near future is very small, it highlights the potential for cosmic catastrophe lurking in seemingly peaceful star systems. The mechanisms behind supernovae push the boundaries of our understanding of physics. The conditions in the core of a collapsing star are so extreme that they can only be approximated in our most powerful computer simulations. Densities reach levels where atomic nuclei are crushed together, and temperatures soar to billions of degrees. In these extreme conditions, exotic forms of matter may briefly exist, and the laws of physics as we understand them are pushed to their limits. One of the most mind-bending aspects of supernova is their role in the production of neutron stars and black holes. Depending on the mass of the progenitor star, a supernova can leave behind a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain on Earth. Even more extreme, if the remnant is massive enough. Not even the pressure of neutron degeneracy can halt the collapse, and a black hole is born. An object so dense that it warps space-time itself, creating a region from which nothing, not even light, can escape. The study of supernovae also intersects with other areas of physics in ways that amplify their cosmic horror potential. For instance, supernovae are thought to be responsible for the production of cosmic rays, high-energy particles that zip through space at nearly the speed of light. These particles, which can have energies millions of times greater than anything we can produce in our most powerful particle accelerators, constantly bombard the Earth. While our atmosphere protects us from most of these cosmic bullets, they serve as a constant reminder of the high-energy physics at play in the cosmos. Supernovae also play a crucial role in the chemical evolution of galaxies. The heavy elements they produce are essential for the formation of planets and the emergence of life as we know it. In a very real sense, we owe our existence to these cosmic explosions. It's a paradoxical and somewhat terrifying thought. The same phenomena that could potentially sterilize planets are also necessary for life to exist in the first place. As we contemplate supernovae, we're forced to confront the violent and transient nature of the cosmos. Stars, which we often think of as eternal and unchanging, can meet spectacular and violent ends. The night sky, seemingly so peaceful, is in fact a battlefield where cosmic violence plays out on an unimaginable scale. Our very existence is predicated on this violence. We are, quite literally, the scattered remnants of long-dead stars. The existence of supernovae also raises profound questions about the nature of the universe and our place in it. In a cosmos where entire stars can be torn apart in an instant, releasing more energy than they've produced in their entire lifetimes, how fragile is our own existence? What other cosmic cataclysms might be lurking, waiting to reshape the universe as we know it? Moreover, supernovae serve as a grim reminder of the life cycle of stars and the ultimate fate that awaits many of the bright points of light we see in the night sky. They are cosmic memento mori, reminding us that even the most massive and brightest stars are doomed to die in spectacular explosions. As we conclude our exploration of supernovae, we're left with a mixture of awe and terror. These cosmic explosions represent both the incredible violence of the universe and its capacity for renewal and creation. They are reminders of how the cosmos operates on scales of energy and time far beyond human comprehension. Yet, paradoxically, we owe our very existence to these cataclysmic events. In the face of such cosmic fireworks, our existence seems both miraculous and precarious. We live in a universe where stars can explode with the energy of billions of suns, where the building blocks of life are forged in the fires of stellar death, and where entire galaxies can be lit up by the death throes of a single star. The supernovae scattered throughout time and space serve as cosmic beacons, illuminating the awesome power and terror of the universe. They remind us that in the grand cosmic scale, creation and destruction are two sides of the same coin. As we continue to study these spectacular stellar explosions, we push the boundaries of our understanding of physics, the life cycles of stars, and the very nature of the universe itself. Dark energy. The force tearing the universe apart. In the pantheon of cosmic horrors, dark energy stands out as perhaps the most enigmatic and terrifying of all. Unlike the violent explosions of supernovae or the crushing gravity of black holes, dark energy operates silently and invisibly on the grandest of scales. It is the unseen force that is quite literally tearing our universe apart, accelerating the expansion of space itself, and driving galaxies away from each other at ever-increasing speeds. To truly grasp the horror of dark energy, we must first understand its nature, or rather, our profound lack of understanding of its nature. Dark energy is, in many ways, the ultimate cosmic mystery. We can't see it, we can't touch it, and we can't directly detect it with any of our instruments. And yet, it appears to make up roughly 68% of the energy content of the observable universe. In other words, the vast majority of the universe is composed of something we can barely comprehend. The discovery of dark energy is a story that reads like cosmic horror in itself. In the late 1990s, two teams of astronomers were studying distant supernovae to measure the expansion rate of the universe. The prevailing theory at the time was that the expansion of the universe, set in motion by the Big Bang, should be slowing down due to the gravitational attraction between galaxies. What they found instead shocked the scientific community to its core. The expansion of the universe was accelerating. This acceleration defied all expectations and violated our understanding of gravity on cosmic scales. It was as if some unseen force was pushing galaxies apart, overwhelming the gravitational attraction that should be pulling them together. This mysterious repulsive force was dubbed dark energy, and its discovery has been hailed as one of the most important astronomical observations of the 20th century. But the terror of dark energy goes far beyond its mysterious nature. Its implications for the fate of our universe are truly the stuff of cosmic nightmares. If dark energy continues to dominate the evolution of the cosmos, as current observations suggest it will, the acceleration will continue indefinitely. Galaxies will be driven further and further apart, eventually moving away from each other faster than the speed of light. This doesn't violate Einstein's special relativity because it's space itself that's expanding. The galaxies aren't moving through space faster than light, but the space between them is growing at a rate that exceeds the speed of light. The end result of this process is truly horrifying. A universe where every galaxy is an island unto itself, completely cut off from the rest of the cosmos. Imagine a night sky devoid of stars, where even the nearest galaxies have receded beyond the cosmic horizon, never to be seen again. This is the ultimate fate that dark energy seems to be driving us towards, a cold, dark, and infinitely lonely universe. It's a future that embodies the essence of cosmic horror, the utter insignificance and isolation of humanity in the face of vast, impersonal cosmic forces. But the horror of dark energy extends beyond its effects on the large-scale structure of the universe. Its very existence challenges our most fundamental understanding of physics. According to quantum field theory, empty space should be teeming with virtual particles popping in and out of existence, creating a sort of vacuum energy. Some physicists have suggested that this vacuum energy could be the source of dark energy. However, when scientists attempt to calculate how much vacuum energy there should be, they arrive at a number that's 120 orders of magnitude larger than the observed value of dark energy. This discrepancy, often called the worst theoretical prediction in the history of physics, hints at a fundamental flaw in our understanding of the universe. It suggests that there's something profoundly wrong with either quantum mechanics or general relativity, or both. The idea that our most successful physical theories might be fundamentally flawed is a source of deep unease for many scientists. Even more unsettling is the possibility that dark energy might not be constant. Some theories suggest that it could change over time, potentially even reversing its effects. If this were to happen, the current expansion of the universe could halt and reverse, leading to a big crunch where all matter collapses back in on itself. Alternatively, if dark energy were to grow stronger over time, it could lead to a big rip, where the repulsive force becomes so strong that it tears apart galaxies, solar systems, planets, and eventually even atoms themselves. The study of dark energy intersects with other areas of physics in ways that amplify its cosmic horror potential. For instance, some theories link dark energy to the idea of multiple universes or the multiverse. In these scenarios, our universe might be just one of many, each with its own laws of physics and values for fundamental constants like dark energy. This raises the terrifying possibility that our universe, with its life-supporting properties, might be an aberration in a vast sea of sterile or hostile universes. Dark energy also plays a crucial role in our understanding of the early universe and cosmic inflation. The theory of inflation posits that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion driven by a form of dark energy. This expansion ironed out any initial inhomogeneities and set the stage for the formation of galaxies and large-scale structures. The idea that the same force that will eventually drive the universe into eternal darkness also played a crucial role in making our existence possible is a cosmic irony of the highest order. Perhaps one of the most disturbing aspects of dark energy is how it limits our ability to observe and understand the universe. As the expansion of the universe accelerates, more and more of the cosmos is being pushed beyond our cosmic horizon, the maximum distance from which light can ever reach us. This means that with each passing moment, we are able to see less and less of the total universe. In a very real sense, dark energy is erasing the cosmos from our view. This limitation on our cosmic perspective raises profound philosophical questions. If we can only ever observe a tiny fraction of the universe, how can we be sure that our theories about the cosmos as a whole are correct? Are we, as some philosophers of science have suggested, forever doomed to have an incomplete picture of reality? The existence of dark energy also challenges our notions of cosmic evolution and the possibility of life in the universe. In a universe dominated by dark energy, galaxies will eventually be so far apart that they will be invisible to each other. Any civilizations arising in such isolated galaxies would have no way of knowing about the existence of other galaxies or the true nature of the cosmos. They would be, in a very real sense, alone in the universe. Moreover, the accelerating expansion driven by dark energy may put fundamental limits on the spread of life and intelligence through the cosmos. As galaxies recede from each other at ever-increasing speeds, interstellar and intergalactic travel become progressively more difficult. There may come a time when it's simply impossible for any civilization, no matter how advanced, to reach other galaxies. The dream of a galaxy-spanning civilization might be forever out of reach, not due to technological limitations, but because of the fundamental nature of the universe itself. As we contemplate dark energy, we're forced to confront the vast scales of space and time over which cosmic processes unfold. The effects of dark energy are imperceptible on human timescales or even the lifetime of our planet or star. It's only when we zoom out to consider billions of years and billions of light years that the true horror of dark energy becomes apparent. This mismatch between human scales and cosmic scales is itself a source of existential dread, highlighting our own cosmic insignificance. Yet paradoxically, it's through our study of dark energy that we've gained some of our most profound insights into the nature of the cosmos. The discovery of dark energy led to a fundamental shift in our understanding of the universe, forcing us to confront the fact that about 95% of the universe, combining dark energy and dark matter, is composed of substances we can't directly observe and don't understand. It's a humbling reminder of how much we have yet to learn about the cosmos. As we conclude our exploration of dark energy, we're left with a mixture of awe and terror. This invisible force, silently working to tear the universe apart, represents both the incredible complexity of the cosmos and the limits of our understanding. It is a reminder that the universe is not just stranger than we imagine, but stranger than we can imagine. In the face of dark energy, our existence seems both miraculous and precarious. We live in a universe that appears fine-tuned for life, yet is dominated by a mysterious force, driving it towards eternal darkness and isolation. As we peer into the depths of space, searching for signs of this enigmatic energy, we must wonder, what other cosmic horrors might be lurking just beyond the limits of our comprehension? The specter of dark energy will continue to haunt our exploration of the cosmos. It represents a form of cosmic horror that is both subtle and profound. Not the explosive violence of supernovae or the crushing power of black holes, but the slow, inexorable driving apart of everything in the universe. As we continue to push the boundaries of our knowledge, dark energy remains a cosmic mystery, challenging our understanding and expanding our cosmic perspective. In the end, dark energy serves as the ultimate cosmic horror, a force we can neither see nor fully understand, yet which determines the fate of everything in existence. It is the embodiment of the vast, impersonal nature of the cosmos, a reminder that the universe operates on scales of space, time, and energy far beyond human comprehension. As we grapple with the implications of dark energy, we are forced to confront our own cosmic insignificance and the terrifying possibility that the ultimate nature of reality may forever remain beyond our grasp. Cosmic strings. Reality-warping space-time defects. In the vast catalogue of cosmic horrors, cosmic strings stand out as particularly mind-bending and terrifying. These hypothetical one-dimensional defects in the fabric of space-time challenge our understanding of physics and the nature of reality itself. Imagine infinitesimally thin lines of pure energy, stretching across the cosmos, capable of slicing entire planets in half and warping the very structure of space and time around them. This is the realm of cosmic strings, where the boundaries between science and cosmic horror blur into a nightmarish tapestry of possibilities. To truly grasp the terror of cosmic strings, we must first delve into their theoretical origins. According to some models of the early universe, as the cosmos cooled and expanded in the moments after the Big Bang, it underwent a series of phase transitions, similar to how water freezes into ice. During these transitions, defects could have formed in the fabric of space-time itself. The most terrifying of these defects are cosmic strings, one-dimensional lines where the universe is still in its high-energy state, relics of the intense conditions that existed just fractions of a second after the birth of the universe. The properties of cosmic strings, as predicted by theory, are truly the stuff of nightmares. These strings would be inconceivably thin, no wider than a proton, yet they would contain unimaginable amounts of mass and energy. A cosmic string just 1 kilometer long would have a mass comparable to that of the entire Earth. This concentration of mass would create a gravitational field around the string so intense that it would warp space-time in bizarre and terrifying ways. One of the most unsettling predictions about cosmic strings is their potential to create closed time-like curves, paths through space-time that loop back on themselves, effectively allowing for time travel. The idea that these cosmic defects could potentially violate causality, allowing effect to precede cause, is deeply disturbing. It challenges our most fundamental understanding of how the universe operates and raises mind-bending paradoxes that even the most advanced physics struggles to resolve. But the horror of cosmic strings extends far beyond their time-warping potential. Their gravitational effects would be equally terrifying. A cosmic string passing between you and a distant light source would create a distinctive double image, as light from behind the string would be bent around it in both directions. More alarmingly, 2 cosmic strings colliding, or a single string looping around itself, could create a gravitational disturbance powerful enough to generate bursts of gravitational waves detectable across cosmic distances. Perhaps the most chilling aspect of cosmic strings is their potential for destruction on a cosmic scale. A cosmic string moving through space would slice through matter like an infinitely sharp knife. Planets, stars, even entire galaxies could be cleaved in two by the passage of a cosmic string. The energy released by such an event would be catastrophic, potentially triggering supernovae or gamma-ray bursts that could sterilize vast swathes of the cosmos. The study of cosmic strings intersects with other areas of cutting-edge physics in ways that amplify their cosmic horror potential. For instance, some theories suggest that cosmic strings could be related to the extra dimensions proposed by string theory. In these models, our three-dimensional universe might be a brane, a membrane floating in a higher dimensional space. Cosmic strings could be points where our brain intersects with others, creating windows into other dimensions or even other universes. This connection to other dimensions raises terrifying possibilities. Could cosmic strings serve as conduits between parallel universes? Might they allow eldritch entities from beyond our realm of existence to intrude into our reality? The idea that these space-time defects could be portals to other worlds or dimensions is a concept straight out of Lovecraftian horror, yet it's grounded in serious scientific speculation. Another disturbing aspect of cosmic strings is their potential role in the formation of structure in the universe. Some theories suggest that the gravitational effects of a network of cosmic strings could have served as seeds for the formation of galaxies and large-scale structures. If true, this would mean that the very structure of our visible universe, the cosmic web of galaxies and voids, could be a result of these terrifying space-time defects. We might owe our very existence to these reality-warping cosmic horrors. The search for cosmic strings pushes the boundaries of our observational capabilities. Their effects on light and gravity could potentially be detected through gravitational lensing or distinctive patterns in the cosmic microwave background radiation. Some scientists have even proposed that fast radio bursts, mysterious millisecond-long pulses of radio waves detected from deep space, could be the result of cosmic string interactions. The idea that we might be witnessing the effects of these cosmic defects without fully understanding what we're seeing adds another layer of cosmic horror to their existence. Perhaps one of the most unsettling aspects of cosmic strings is how they challenge our notions of the stability and predictability of the universe. If these defects in space-time exist, they suggest that the fabric of reality itself is flawed, containing scars from its turbulent birth. The universe, rather than being a stable and unchanging backdrop to existence, becomes a dynamic and potentially dangerous environment, where the very structure of space-time could be disrupted by these wandering lines of primordial energy. The concept of cosmic strings also raises profound questions about the nature of the vacuum and the true ground state of the universe. If cosmic strings are indeed regions where space-time remains in a high-energy state from the early universe, could they potentially decay to a lower energy state? Some theories suggest that such a decay could trigger a phase transition that would propagate at the speed of light, effectively rewriting the laws of physics in its wake. The idea that the fundamental constants and laws that govern our reality could be suddenly and catastrophically altered is perhaps the ultimate cosmic horror. As we contemplate cosmic strings, we're forced to confront the possibility that our understanding of the universe is profoundly incomplete. These hypothetical defects in space-time serve as a constant reminder of how much we have yet to learn about the fundamental nature of reality. They suggest that the universe is far stranger and more complex than we can currently comprehend, with layers of structure and energy beyond our current perception or understanding. The existence of cosmic strings, if confirmed, would have profound implications for our understanding of the early universe and the nature of space-time itself. They would provide a unique window into the conditions that existed in the first fractions of a second after the Big Bang, potentially allowing us to probe energies and scales far beyond the reach of any particle accelerator we could ever build on Earth. Yet, this potential for scientific discovery comes with a terrifying caveat. If cosmic strings do exist, they represent a cosmic threat unlike any other we've encountered. Unlike the slowly encroaching darkness of cosmic expansion or the localized destruction of black holes and supernovae, cosmic strings could potentially disrupt the very fabric of reality itself. They are cosmic juggernauts, barreling through the universe with unimaginable energy, indifferent to the destruction they might cause. The horror of cosmic strings also extends to their potential technological applications. Some speculative theories suggest that a sufficiently advanced civilization might be able to manipulate or even create cosmic strings. The energy contained in even a small segment of cosmic string is beyond anything we can currently imagine harnessing. A civilization capable of utilizing this energy would wield power on a truly cosmic scale. The idea that such power might exist in the universe, potentially in the hands of alien intelligences with motives we cannot fathom, is a source of both wonder and deep existential dread. As we conclude our exploration of cosmic strings, we're left with a mixture of awe and terror. These hypothetical defects in the fabric of space-time represent both the incredible complexity of the cosmos and the vast unknowns that still exist in our understanding of physics. They are reminders that the universe is not just stranger than we imagine, but stranger than we can imagine. In the face of such cosmic phenomena, our existence seems both miraculous and precarious. We live in a universe that might be threaded through with unimaginably energetic defects in space-time itself, capable of slicing through worlds and warping the very nature of causality. As we peer into the depths of space, searching for signs of these elusive cosmic strings, we must wonder, what other mind-bending horrors might be lurking in the fabric of reality itself? The specter of cosmic strings serves as a stark reminder of the vast, impersonal, and potentially hostile nature of the cosmos. They embody a form of cosmic horror that transcends the merely physical, challenging our most fundamental assumptions about the nature of reality. As we continue to push the boundaries of our knowledge, the possibility of cosmic strings looms large, a cosmic sword of Damocles hanging over our understanding of the universe. In the end, whether cosmic strings turn out to be real or remain a theoretical curiosity, their very conception highlights the awesome and terrifying nature of the cosmos we inhabit. They serve as a humbling reminder of how much we have yet to learn about the universe and of the mind-bending possibilities that might exist in the depths of reality. False vacuum decay, the universe's self-destruct button. In the pantheon of cosmic horrors, few concepts are as existentially terrifying as false vacuum decay. This theoretical phenomenon represents not just a threat to life as we know it, but a fundamental instability in the very fabric of reality. Imagine a cosmic catastrophe that could unravel the laws of physics themselves, spreading at the speed of light to consume everything in existence. This is the nightmare scenario of false vacuum decay, often described as the universe's own self-destruct button. To truly grasp the horror of false vacuum decay, we must first delve into the bizarre world of quantum field theory and the nature of the vacuum itself. In quantum physics, the vacuum is not truly empty. Instead, it's a seething cauldron of virtual particles popping in and out of existence, their energies carefully balanced to maintain the apparent emptiness of space. This quantum vacuum has an associated energy state, and herein lies the potential for cosmic catastrophe. The terrifying possibility arises from the idea that our current vacuum state might not be the lowest possible energy state. Just as a ball resting on a hillside is in a state of apparent stability, but could roll down to a lower energy state, our entire universe might be in a similar situation. We could be living in what's called a false vacuum, a metastable state that appears stable but is actually precariously balanced, hiding the true lower energy vacuum state beneath. The horror of this situation becomes apparent when we consider what would happen if a small region of the universe were to tunnel through to this true vacuum state. This transition would release an enormous amount of energy, creating a bubble of true vacuum that would expand outward at the speed of light. Inside this bubble, the laws of physics as we know them would be fundamentally different. The constants that govern the behavior of matter and energy, things like the strengths of fundamental forces and the masses of particles, would be altered. The implications of such an event are truly the stuff of cosmic nightmares. As this bubble expanded, it would consume everything in its path. Atoms would disintegrate, unable to hold together under the new laws of physics. Stars would wink out of existence. Even the fabric of space-time itself would be radically altered. And because this bubble would expand at the speed of light, we would have no warning of its approach. One moment, the universe would exist as we know it. The next, reality itself would unravel. What makes false vacuum decay particularly terrifying is its potential to be triggered by quantum fluctuations. In theory, at any moment, anywhere in the universe, a quantum fluctuation could cause a tiny region of space to tunnel to the true vacuum state, initiating this cosmic apocalypse. It's as if the universe is a minefield, and we're living our lives unaware that any step could trigger the ultimate catastrophe. The study of false vacuum decay intersects with other areas of physics in ways that amplify its cosmic horror potential. For instance, some theories suggest that the early universe went through a series of phase transitions as it cooled, each representing a decay from one false vacuum to another. This raises the chilling possibility that our current universe is just one in a series of cosmic epochs, each with its own distinct laws of physics, separated by cataclysmic vacuum transitions. Moreover, the concept of false vacuum decay ties into ideas about the multiverse. In some models, different regions of the multiverse could be in different vacuum states. Our observable universe might be a bubble of false vacuum floating in a sea of true vacuum, or vice versa. This cosmic foam of realities, each with its own physical laws, suggests a universe far stranger and more precarious than we ever imagined. The possibility of false vacuum decay also raises profound questions about the nature of existence and the apparent fine-tuning of our universe. The fact that we exist in a universe where the laws of physics allow for complex structures like galaxies, stars, and life suggests that our vacuum state, false though it may be, is remarkably stable. Some physicists have even suggested that the apparent fine-tuning of our universe's constants might be a result of vacuum selection. The idea that only universes with sufficiently stable vacuums can develop complex structures and potentially conscious observers. This idea, while offering a potential explanation for our universe's apparent hospitability to life, comes with its own existential terror. It suggests that we might be living in a cosmic bubble of improbable stability, surrounded by a multiverse of realities hostile to our very existence. Our universe, rather than being a safe harbor for life, becomes a fragile oasis of complexity in a vast cosmic desert of simple, high-energy states. Perhaps one of the most unsettling aspects of false vacuum decay is how it challenges our notions of cosmic eschatology. Many models of the far future of the universe envision a slow decline into entropy, the heat death scenario where the universe expands and cools into eternal darkness. False vacuum decay offers a different and in many ways more terrifying end. Instead of a slow fade into oblivion, it presents the possibility of a sudden, unpredictable, and total annihilation of everything we know. The concept of false vacuum decay also intersects with cutting-edge particle physics in ways that bring this cosmic horror unsettlingly close to home. The discovery of the Higgs boson in 2012 allowed physicists to calculate the stability of our vacuum with unprecedented precision. Some calculations suggest that our vacuum might indeed be metastable, given the measured mass of the Higgs boson. While the timescale for any potential decay is likely to be far longer than the current age of the universe, the very possibility that we might be living in a false vacuum adds a layer of cosmic precariousness to our existence. Even more alarming are speculations about how false vacuum decay might be artificially triggered. Some highly speculative theories suggest that extremely high-energy particle collisions, beyond anything we can currently achieve, might be capable of nucleating a bubble of true vacuum. While such scenarios are considered highly unlikely and are well beyond our current technological capabilities, they raise ethical questions about the risks of probing the fundamental nature of reality. As we contemplate false vacuum decay, we're forced to confront the possibility that the very foundations of reality are not as solid as we once thought. The laws of physics, which we often think of as immutable and eternal, might be more like local bylaws, applicable only to our small bubble of existence and subject to catastrophic change. This realization strips away any sense of cosmic security, leaving us exposed to the whims of quantum fluctuations that could, at any moment, rewrite the very rules of existence. The existential dread inspired by false vacuum decay is compounded by its undetectability and unpredictability. Unlike many cosmic threats that we might see coming, asteroid impacts, nearby supernovae, or even the slow expansion of the universe, a false vacuum decay event would give no warning. We would not even have time to realize what was happening before our very atoms were torn apart by the changing laws of physics. This absolute lack of control or forewarning taps into some of our deepest existential fears. Yet paradoxically, the study of false vacuum decay and the nature of the quantum vacuum has led to some of our most profound insights into the nature of reality. It highlights the deep connections between the very large, cosmology, and the very small, quantum physics. It forces us to grapple with questions about the nature of existence itself. Why does anything exist at all? Why these particular laws of physics and not others? Are the fundamental constants of nature truly constant, or are they subject to change? As we conclude our exploration of false vacuum decay, we're left with a mixture of awe and terror. This potential instability in the very fabric of reality represents both the incredible complexity of the cosmos and the vast unknowns that still exist in our understanding of physics. It is a reminder that the universe is not just stranger than we imagine, but stranger than we can imagine. In the face of such a cosmic threat, our existence seems both miraculous and precarious. We live in a universe that might be fundamentally unstable, where the continued existence of reality as we know it could depend on the quantum equivalent of a coin balanced on its edge. As we peer into the depths of the quantum vacuum, searching for a deeper understanding of the nature of reality, we must wonder, are we opening Pandora's box? What other reality-shattering horrors might be lurking in the foundations of existence itself? The specter of false vacuum decay serves as the ultimate cosmic horror, a threat not just to our existence but to existence itself. It embodies the vast, impersonal, and potentially hostile nature of the cosmos on its most fundamental level. As we continue to push the boundaries of our knowledge, exploring the nature of the vacuum and the foundations of reality, the possibility of false vacuum decay looms large, a cosmic sword of Damocles hanging over not just our universe, but potentially all of existence. In the end, whether false vacuum decay turns out to be a real threat or remains a theoretical curiosity, its very conception highlights the awesome and terrifying nature of the cosmos we inhabit. It serves as a humbling reminder of how much we have yet to learn about the universe and of the mind-bending possibilities that might exist in the depths of reality. In contemplating false vacuum decay, we confront a cosmic horror that challenges not just our existence, but our very understanding of what existence means. Time dilation and relativity. The horror of subjective time. In the vast tapestry of cosmic horrors, few concepts are as profoundly unsettling as time dilation and the principles of relativity. These fundamental aspects of our universe challenge our most basic intuitions about reality, revealing a cosmos where time itself is malleable, subject to the warping effects of gravity and motion. The implications of these phenomena stretch far beyond mere physical curiosities, touching on the very nature of existence and our place within the fabric of space-time. To truly grasp the horror of time dilation, we must first understand its origins in Einstein's theories of special and general relativity. These revolutionary ideas shattered the Newtonian concept of absolute time, revealing instead a universe where time is relative, flowing at different rates for different observers depending on their relative motion or their proximity to massive objects. The special theory of relativity tells us that as an object approaches the speed of light, time for that object slows down relative to a stationary observer. This effect, known as time dilation, becomes pronounced at velocities close to the speed of light. Imagine two twins, one who remains on Earth and another who embarks on a journey at near light speed. When the traveling twin returns, she would find that she has aged much less than her Earth-bound sibling. This twin paradox is not merely a thought experiment, but a real effect that has been measured with atomic clocks on fast-moving aircraft and satellites. The general theory of relativity extends this concept to the realm of gravity. Near massive objects like black holes, where space-time is severely curved, time moves more slowly than in regions of weaker gravity. An observer falling into a black hole would experience time very differently from an observer watching from a safe distance. As the infalling observer approaches the event horizon, time for them would slow to a crawl relative to the outside universe. The horror of time dilation lies not just in its reality-bending effects, but in the profound existential implications it carries. It reveals a universe where the flow of time is not a constant universal stream, but a subjective experience that can vary dramatically depending on one's circumstances. This subjectivity of time strikes at the heart of our perception of reality and our place within it. Consider the fate of an astronaut falling into a black hole. As they approach the event horizon, they would witness the entire future history of the universe unfold before their eyes in a matter of moments. Stars would live and die, galaxies would collide and disperse, and the universe itself would age towards its heat death, all while the astronaut experienced only a brief passage of time. Yet from the perspective of an outside observer, the astronaut would appear frozen in time at the event horizon, slowly fading from view over millions of years. This scenario, often called the black hole information paradox, highlights the horror of subjective time. It suggests a universe where different observers can experience radically different realities, where the very concept of simultaneity breaks down. The idea that there is no universal now, no single moment that all observers can agree upon, is deeply unsettling to our intuitive understanding of reality. The implications of time dilation extend far beyond theoretical physics, touching on profound philosophical questions. If time is subjective, what does that mean for our concept of free will? If the future already exists from the perspective of a highly accelerated observer, does that imply a deterministic universe where all events are predestined? These questions challenge our most fundamental notions of causality and agency. Moreover, Time dilation raises disturbing questions about the nature of consciousness and personal identity. If an observer near a black hole experiences millennia in what seems like moments to them, how does that affect their subjective experience of consciousness? Would their mind be able to process the apparent rapid aging of the universe, or would they experience a form of cognitive breakdown? The idea that our consciousness, our very sense of self, might be as malleable as time itself is a source of deep existential dread. The horror of time dilation is amplified when we consider its potential impact on space exploration and the search for extraterrestrial life. Any long-distance space travel at relativistic speeds would result in significant time dilation. A crew on a decades-long interstellar journey might return to find centuries or millennia have passed on Earth. The psychological impact of such temporal displacement, of returning to a world where everyone and everything you knew has long since turned to dust, is almost unimaginable. This time debt of relativistic travel also presents a terrifying obstacle to any potential galactic civilization. Different regions of such a civilization would effectively exist in different time frames, making coherent communication and governance nearly impossible. The very forces that allow us to contemplate traveling to the stars also ensure that we can never truly conquer the vast gulfs of time that separate cosmic objects. The study of time dilation intersects with other areas of physics in ways that amplify its cosmic horror potential. For instance, quantum mechanics introduces its own form of time weirdness through phenomena like quantum entanglement, where particles can seemingly influence each other instantaneously across vast distances. The tension between the time dilation of relativity and the apparent timelessness of quantum effects is a source of ongoing mystery and speculation in physics. Perhaps one of the most unsettling aspects of time dilation is how it challenges our notions of past, present, and future. In relativity, these concepts become much more fluid than our everyday experience suggests. Events that are in the future for one observer might be in the past for another, depending on their relative motion. This relativity of simultaneity suggests a block universe model where all of time, past, present, and future, exists as a four-dimensional space-time block. In this view, our perception of a flowing time is merely an illusion, a result of our limited perspective within this eternal, unchanging structure. This block universe concept is profoundly disturbing. It suggests that our sense of agency, our feeling of making decisions and affecting the future, might be nothing more than an illusion. If all of time already exists, eternally and unchangingly, then are we merely playing out predetermined roles in a cosmic script? The idea that our lives might be more akin to characters in a novel, our stories already written from cover to cover, than autonomous agents shaping our destinies is a source of deep existential anxiety. The effects of time dilation, while most pronounced in extreme scenarios like near light-speed travel or the vicinity of black holes, are not confined to these cosmic scales. Even in our everyday lives, we are subject to tiny amounts of time dilation. GPS satellites, for instance, need to account for time dilation effects to maintain their accuracy. The fact that time can flow at different rates even in our familiar earthbound existence adds an element of cosmic eeriness to our daily lives. Moreover, time dilation affects our understanding of cosmic history and the age of the universe itself. The 13.8 billion years since the Big Bang is a measure from our particular reference frame. From the perspective of a photon traveling at the speed of light, no time passes at all. For such a particle, the beginning and end of the universe would be a single instant. This extreme subjectivity of cosmic history adds another layer of uncertainty to our place in the grand narrative of the cosmos. As we conclude our exploration of time dilation and relativity, we're left with a mixture of awe and terror. These fundamental aspects of our universe represent both the incredible complexity of the cosmos and the vast unknowns that still exist in our understanding of reality. They are reminders that the universe is not just stranger than we imagine, but stranger than we can imagine. In the face of such cosmic phenomena, our existence seems both miraculous and precarious. We live in a universe where time itself is a fluid, subjective experience, where the future and past can blur depending on one's perspective, and where our most fundamental notions of cause and effect can break down. As we peer into the depths of space-time, grappling with the implications of relativity, we must wonder what other mind-bending horrors might be lurking in the very fabric of reality itself. the specter of time dilation serves as a stark reminder of the vast, impersonal, and fundamentally alien nature of the cosmos. It embodies a form of cosmic horror that transcends the merely physical, challenging our most basic assumptions about the nature of existence. As we continue to push the boundaries of our knowledge, exploring the nature of time and the structure of space-time, the implications of relativity loom large, a cosmic memento mori, reminding us of the fleeting and subjective nature of our temporal existence. In the end, time dilation and relativity highlight the awesome and terrifying nature of the cosmos we inhabit. They serve as a humbling reminder of how much we have yet to learn about the universe and of the mind-bending possibilities that might exist in the depths of reality. Antimatter, the mirror universe that could annihilate us. In the pantheon of cosmic horrors, antimatter stands out as a phenomenon that is both tantalizingly close to our everyday reality and yet profoundly alien and destructive. It is the stuff of science fiction, yet it is also a scientifically proven reality that challenges our understanding of the universe and poses existential questions about the nature of existence itself. Antimatter is, in essence, the mirror image of ordinary matter. For every particle of matter, there exists an antimatter counterpart with the same mass but opposite charge. Electrons have positrons, protons have antiprotons, and neutrons have antineutrons. These antiparticles are not merely theoretical constructs. They have been observed and even manufactured in particle accelerators. The true horror of antimatter lies in its interaction with ordinary matter. When matter and antimatter collide, they annihilate each other in a burst of pure energy, converting their entire mass into radiation according to Einstein's famous equation E equals mc squared. This reaction is the most efficient energy conversion process known to physics, releasing orders of magnitude more energy than nuclear fission or fusion. To grasp the terrifying potential of antimatter, consider this. A single gram of antimatter annihilating with a gram of matter would release energy equivalent to a nuclear bomb. The entire city of New York could be powered for a day with just 25 milligrams of antimatter. The destructive potential is so great that antimatter has been seriously considered as a potential component in theoretical planet-destroying weapons. But the horror of antimatter extends far beyond its potential for destruction. Its very existence poses profound questions about the nature of our universe. According to our best theories, the Big Bang should have produced equal amounts of matter and antimatter. Yet, the observable universe appears to be composed almost entirely of matter. This asymmetry, known as the baryon asymmetry problem, is one of the greatest unsolved mysteries in physics. The implications of this asymmetry are staggering. Why does our universe favor matter over antimatter? Is there a fundamental difference between the two that we don't yet understand? Or is it possible that vast regions of antimatter exist somewhere in the cosmos, separated from us by immense voids of space? The idea that half of the universe could be made of antimatter, forever inaccessible and deadly to us, is a source of both wonder and existential dread. This possibility of large-scale antimatter structures in the universe is not just idle speculation. Some scientists have proposed that some of the gamma-ray bursts we observe could be the result of matter-antimatter annihilations on a cosmic scale. Imagine entire galaxies of antimatter, mirror images of our own, that would obliterate anything from our matter-based realm that strayed too close. The search for cosmic antimatter adds another layer to this cosmic horror. Scientists have developed ingenious methods to detect antimatter in cosmic rays and to search for signatures of antimatter galaxies. So far, these searches have come up empty, deepening the mystery. Are we truly alone in a matter-dominated universe, or is antimatter lurking just beyond our ability to detect it? The study of antimatter intersects with other areas of physics in ways that amplify its cosmic horror potential. For instance, some theories suggest that antimatter might interact with gravity differently than ordinary matter, potentially even exhibiting anti-gravity. If true, this would not only challenge our understanding of one of the fundamental forces of nature, but could also have profound implications for the structure and evolution of the universe. Consider the mind-bending implications if antimatter did indeed fall up, instead of down in a gravitational field. This would mean that in an antimatter-dominated region of space, the very nature of cosmic structures would be inverted. Antimatter stars might expel their fuel outward instead of compressing it inward, leading to entirely different stellar life cycles. Antimatter planets might hover above their suns rather than orbiting them. The very concept of falling would be turned on its head. Another terrifying possibility arises from the intersection of antimatter with quantum mechanics. The phenomenon of quantum tunneling suggests that there's a non-zero probability of particles spontaneously converting into their antiparticles. While the odds of this happening on a macroscopic scale are infinitesimally small, the mere possibility that the atoms in your body could suddenly become antimatter and annihilate with their surroundings is the stuff of quantum nightmares. Imagine for a moment the horror of such a scenario. You're going about your daily life when suddenly, without warning, a small region of your body undergoes this impossible quantum transformation. In less than an instant, before you could even register what's happening, that tiny speck of antimatter would annihilate with the surrounding matter, releasing energy equivalent to a small nuclear explosion. The absurdly low probability of such an event is cold comfort in the face of its horrific consequences. The existence of antimatter also raises disturbing questions about the nature of life and consciousness. If antimatter is truly the mirror image of matter, could there be antimatter-based life forms somewhere in the universe? What would such life look like? Would an antimatter brain be capable of consciousness? These questions push at the boundaries of our understanding of life and mind, suggesting the possibility of forms of existence utterly alien and inaccessible to us. Consider the philosophical implications of antimatter life. If it exists, it would be fundamentally incompatible with our form of life, unable to interact with us in any meaningful way without mutual annihilation. This raises profound questions about the nature of life itself. Is the matter-antimatter division a more fundamental categorization of life than any biological classification we might conceive? Could there be entire ecosystems, civilizations, or even galactic empires composed of antimatter, forever separated from us by the deadly barrier of annihilation? Perhaps one of the most unsettling aspects of antimatter is how it challenges our notions of substance and void. We typically think of empty space as being, well, empty. But quantum field theory tells us that even the vacuum of space is seething with virtual particles and antiparticles constantly popping in and out of existence. This quantum foam is usually hidden from our everyday experience, but it suggests a universe far stranger and more active than we typically imagine. The concept of the quantum vacuum and its relationship to antimatter is a source of both wonder and existential dread. It suggests that the very fabric of space-time is not a passive stage on which the drama of the cosmos plays out, but an active, roiling sea of potential. Every point in space, even in the deepest voids between galaxies, is alive with the possibility of matter and antimatter springing into existence. This quantum foam also leads to one of the most perplexing predictions in all of physics: vacuum decay. Some theories suggest that our universe might be in a false vacuum state, like a ball resting on a small hill, rather than in the lowest valley. If a bubble of true vacuum were to form, perhaps nucleated by an antimatter fluctuation, it could expand at the speed of light, obliterating everything in its path, and fundamentally altering the laws of physics. The idea that the vacuum itself might be unstable, capable of spawning an apocalyptic event at any moment, is truly the stuff of cosmic nightmares. The potential applications of antimatter, while exciting, also carry their own horrors. Antimatter could theoretically be used as an incredibly efficient fuel source, enabling deep space exploration. But the challenges of producing, containing, and utilizing antimatter are enormous. A single antiparticle out of place could trigger a catastrophic reaction. The idea of antimatter-powered spacecraft is thrilling, but it's also terrifying, like flying a rocket fueled by miniature nuclear bombs. Imagine the horror of an antimatter containment failure on such a spacecraft. The crew would have mere moments to react before the escaping antimatter contacted the ship's matter structure, triggering a cascade of annihilations that would vaporize the entire vessel in a burst of gamma radiation. The risks involved in such technology are almost unimaginable, yet the potential rewards in terms of space exploration and energy production might one day drive us to take those risks. The study of antimatter has also led to the development of new medical technologies, particularly in the field of medical imaging. Positron emission tomography, or PET, scans use the annihilation of positrons, anti-electrons, to create detailed images of biological processes within the body. It's a striking example of how the most exotic and terrifying aspects of the cosmos can be harnessed for beneficial purposes. Yet even here, there's an element of cosmic horror. Every PET scan involves creating tiny amounts of antimatter within the human body, walking a careful line between medical benefit and potential annihilation. As we contemplate antimatter, we're forced to confront the fragility of our existence. We live in a universe where an invisible, intangible substance could instantly annihilate us if we were to encounter it. Our very atoms are in a precarious balance, saved from annihilation only by the apparent scarcity of antimatter in our cosmic neighborhood. This precariousness extends to the very earliest moments of our universe. The fact that we exist at all is due to a tiny imbalance in the amounts of matter and antimatter produced in the Big Bang. Had the ratio been exactly equal, all matter and antimatter would have annihilated, leaving behind a universe of pure radiation. Our entire cosmic history, the formation of stars and galaxies, the evolution of life, the development of consciousness, all of it hinges on this primordial asymmetry that we still don't fully understand. Yet, paradoxically, the study of antimatter has led to some of our most profound insights into the nature of the universe. It has pushed the boundaries of our technology, leading to the development of incredible machines like particle accelerators and antimatter traps. It has forced us to grapple with fundamental questions about symmetry and asymmetry in nature, about the origins of the universe, and about the nature of existence itself. The discovery of antimatter itself reads like a cosmic horror story. When Paul Dirac first predicted the existence of antimatter in 1928, he was reluctant to publish his findings because they seemed too bizarre. The idea that every particle has an antimatter twin, and that this twin could annihilate it in a burst of pure energy, seemed like something out of science fiction. Yet within a few years, positrons were discovered in cosmic rays, confirming Dirac's prediction and opening up a new chapter in our understanding of the universe. This history serves as a humbling reminder of how strange reality can be, often outstripping our wildest imaginations. It suggests that there may be other aspects of the cosmos, equally bizarre and potentially terrifying, that we have yet to discover or even conceive of. The horror of antimatter lies not just in its destructive potential, but in how it undermines our intuitive understanding of reality. It suggests a universe that is far more complex, far more precarious, and far more mysterious than we ever imagined. It is a reminder that the cosmos is not just stranger than we suppose, but stranger than we can suppose. Antimatter also plays a role in some of the most extreme environments in the universe. In the intense magnetic fields around neutron stars, scientists believe that virtual photons from the quantum vacuum can spontaneously convert into electron-positron pairs. These charged particles, accelerated by the star's magnetic field, produce the powerful beams of radiation we observe as pulsars. The idea that antimatter plays a crucial role in these cosmic lighthouses, born from the death throes of massive stars, adds another layer of awe and terror to our understanding of the cosmos. As we conclude our exploration of antimatter, we're left with a mixture of awe and terror. This mirror image matter represents both the incredible complexity of the cosmos and the vast unknowns that still exist in our understanding of physics. It is a reminder that the universe is not just stranger than we imagine, but potentially more dangerous and unstable than we can comprehend. In the face of such a cosmic phenomenon, our existence seems both miraculous and utterly fragile. We live in a universe where the very stuff of existence has an evil twin, a doppelganger that could unmake us in an instant. As we peer into the depths of particle physics and cosmology, grappling with the implications of antimatter, we must wonder, what other fundamental aspects of reality might we be overlooking? What other cosmic horrors might be lurking in the very fabric of existence? The specter of antimatter serves as a stark reminder of the vast, impersonal, and potentially hostile nature of the cosmos. It embodies a form of cosmic horror that transcends the merely physical, challenging our most basic assumptions about the nature of reality. As we continue to push the boundaries of our knowledge, exploring the nature of matter and antimatter, we confront a universe that is both terrifyingly hostile and unimaginably wondrous. In the end, antimatter reminds us that we live in a universe poised on a knife edge of existence. The very fact that we're here to contemplate these mysteries is the result of a cosmic balancing act that we're only beginning to understand. As we face the terror of antimatter, we also embrace the profound mystery of our existence, forever seeking to unravel the secrets of a universe that never ceases to amaze and frighten us in equal measure. Quantum entanglement, spooky action, and the death of local reality. In the vast pantheon of cosmic horrors, few phenomena are as profoundly unsettling as quantum entanglement. This cornerstone of quantum mechanics challenges our most fundamental notions of reality, causality, and the nature of existence itself. It suggests a universe that is not just strange, but fundamentally interconnected in ways that defy our classical intuitions and push the boundaries of what we consider possible. Quantum entanglement occurs when particles interact in such a way that the quantum state of each particle cannot be described independently, even when the particles are separated by a large distance. Instead, a quantum state must be described for the system as a whole. This leads to correlations between observable physical properties of the systems that, according to the Copenhagen interpretation of quantum mechanics, do not have definite values until they are measured. The horror of quantum entanglement lies not just in its counterintuitive nature, but in its implications for our understanding of reality itself. Einstein famously referred to it as spooky action at a distance because it seemed to suggest that information could travel faster than light, violating the fundamental principles of his theory of relativity. The idea that the universe might operate in ways that violate our deepest intuitions about cause and effect is truly the stuff of cosmic nightmares. To grasp the terrifying implications of quantum entanglement, consider the classic example of entangled particles. If we create a pair of particles with opposite spins and separate them by a vast distance, say placing them on opposite sides of the galaxy, quantum mechanics tells us that measuring the spin of one particle instantly determines the spin of the other, regardless of the distance between them. This seems to suggest a kind of cosmic interconnectedness that transcends space and time as we understand them. The existential dread induced by this realization is profound. It implies that the very fabric of reality is woven from threads that stretch across the cosmos, connecting every particle to every other particle in ways that defy our understanding of space and time. The boundaries we perceive between objects, between ourselves and the world, may be far more porous and illusory than we ever imagined. In a very real sense, we may be entangled with the farthest reaches of the universe, our fate intertwined with cosmic events beyond our comprehension. One of the most unsettling aspects of quantum entanglement is how it challenges our notion of local realism. Local realism is the intuitive idea that objects have definite properties, whether or not they are observed, and that influences cannot travel faster than light. Quantum entanglement seems to violate at least one of these principles. Either the properties of entangled particles are not definite until measured, violating realism, or there is some kind of instantaneous influence between the particles, violating locality. Either option is profoundly disturbing to our classical intuitions about how the universe should work. The implications of quantum entanglement are truly the stuff of cosmic horror. It suggests that the universe is not local, that is, that what happens here can instantaneously affect what happens there, regardless of the distance involved. This non-locality flies in the face of our everyday experience and our deep-seated notions of cause and effect. It implies a universe where the very concept of here and there breaks down at the fundamental level, where the fabric of space-time itself may be an emergent property rather than a fundamental aspect of reality. Even more disturbing is what quantum entanglement implies about the nature of reality itself. According to some interpretations of quantum mechanics, particles don't have definite properties until they're measured. This suggests that reality is not just observer-dependent, but that it may not exist in a definite state until it's observed. The implications of this for our understanding of free will, consciousness, and the nature of existence itself are profound and deeply unsettling. The horror of quantum entanglement extends to its potential applications. Quantum entanglement is a key principle behind quantum computing, a technology that promises to revolutionize computation by allowing for the processing of vast amounts of information simultaneously. While this has exciting potential applications, it also poses existential threats to current encryption methods, potentially rendering all current digital security obsolete overnight. Moreover, quantum entanglement opens the door to other seemingly magical technologies, such as quantum teleportation. While this doesn't allow for the transportation of matter in the way science fiction often portrays, it does allow for the perfect transmission of quantum states over arbitrary distances. The idea that the fundamental state of a particle could be instantaneously transmitted across vast distances challenges our notions of privacy and the limits of information transfer. The study of quantum entanglement intersects with other areas of physics in ways that amplify its cosmic horror potential. For instance, some theories suggest that the phenomenon of quantum entanglement might be the key to understanding gravity and unifying quantum mechanics with general relativity. The ER=EPR conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that entanglement and wormholes might be two sides of the same coin. This raises the mind-bending possibility that the spooky connections of quantum entanglement might be literal tunnels through space-time. Another terrifying implication of quantum entanglement arises from its intersection with the many worlds interpretation of quantum mechanics. This interpretation suggests that every quantum event creates a branching of reality into multiple universes. When combined with entanglement, this leads to the possibility of quantum immortality. The idea that from the perspective of a conscious observer, they might never experience death because their consciousness always follows the branch of reality where they survive. Perhaps one of the most unsettling aspects of quantum entanglement is how it challenges our notions of individuality and separateness. If particles can be entangled, maintaining their connection even when separated by vast distances, what does this mean for our concept of individual identity? Some philosophers and scientists have even suggested that consciousness itself might be a product of quantum entanglement in the brain, raising profound questions about the nature of mind and self. The phenomenon of quantum entanglement also intersects with cosmology in ways that amplify its cosmic horror potential. Some theories suggest that the entire universe might be entangled, a concept known as cosmic quantum entanglement. This would mean that every particle in the universe is connected to every other particle in some way, creating a cosmic web of quantum connections that transcends space and time. As we contemplate quantum entanglement, we're forced to confront the possibility that our understanding of reality is profoundly incomplete. The seemingly solid, separate, and locally real world we experience in our everyday lives may be an illusion, a macroscopic approximation of a quantum reality that is fundamentally interconnected, probabilistic, and observer-dependent. This realization strips away any sense of cosmic security, leaving us exposed to a reality far stranger and more malleable than we ever imagined. Yet paradoxically, the study of quantum entanglement has led to some of our most profound technological advancements. Quantum cryptography promises unbreakable codes, while quantum sensors offer unprecedented levels of precision. The development of quantum computers, based on the principles of superposition and entanglement, may revolutionize fields from drug discovery to financial modeling. In this way, the cosmic horror of quantum entanglement becomes a source of both terror and promise. As we conclude our exploration of quantum entanglement, we're left with a mixture of awe and existential dread. This quantum phenomenon represents both the incredible complexity of the cosmos and the vast unknowns that still exist in our understanding of reality. It is a reminder that the universe is not just stranger than we imagine, but stranger than we can imagine. In the face of quantum entanglement, our existence seems both miraculous and precarious. We live in a universe where the very fabric of reality is woven from quantum threads that defy our classical intuitions. As we peer into the depths of the quantum realm, grappling with the implications of entanglement, we must wonder, what is the true nature of reality? Are we living in a cosmic web of quantum connections, our fates entangled with every other particle in the universe? The specter of quantum entanglement serves as the ultimate cosmic horror, a phenomenon that challenges not just our understanding of physics, but our very conception of reality, causality, and existence. It embodies the vast, interconnected, and fundamentally alien nature of the quantum world. Heat death, the slow fade to eternal darkness. In the vast pantheon of cosmic horrors, few concepts are as profoundly unsettling as the heat death of the universe. This ultimate fate, also known as the Big Freeze, represents not just an end to life as we know it, but the final whimper of existence itself. It is a future of unimaginable bleakness, where the universe fades not with a bang, but with an eternal ice-cold whisper. To truly grasp the horror of the heat death, we must first understand its origins in the laws of thermodynamics. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. In simpler terms, the universe tends towards disorder. Energy disperses, useful work becomes increasingly difficult to perform, and the cosmic clock winds down towards a state of perfect equilibrium. The concept of heat death arises from extrapolating this principle to its ultimate conclusion. As the universe continues to expand and cool, it will eventually reach a state where all usable energy has been exhausted. Stars will burn out, black holes will evaporate, and even the atoms themselves will decay. What remains is a vast, cold emptiness where the temperature approaches absolute zero and no further work or change is possible. The timeline for this process is almost beyond comprehension. We're not talking about millions or billions of years, but trillions upon trillions of years. Long after the last stars have flickered out, long after the galaxies have dissolved into a thin soup of fundamental particles, the universe will continue its slow march towards absolute zero. The stages of this cosmic decline are a crescendo of existential horror. First, star formation will cease as the available gas becomes too diffuse to collapse into new stellar nurseries. The existing stars will slowly burn through their fuel, with the smallest and dimmest lasting the longest. Our own sun has about 5 billion years left, but the tiniest red dwarf stars might shine for trillions of years. As the stars die out, the universe will grow darker and colder. Planets will freeze over, and any remaining life will be forced to huddle around the dying embers of the cosmos. The galaxies themselves will begin to dissolve as their stars are flung into intergalactic space through gravitational interactions. But even this is just the beginning of the end. Over incomprehensibly long timescales, even the most stable structures in the universe will decay. Planets and other large bodies will eventually evaporate into space, atom by atom. Black holes, once thought to be eternal, will slowly radiate away their mass through Hawking radiation. The largest supermassive black holes might last for up to 10 to the power of 100 years. But eventually, they too will dissipate into the void. In the unimaginably distant future, even the protons and neutrons that make up atomic nuclei will decay. The universe will be reduced to a thin gruel of electrons, positrons, and photons, all of such low energy that no meaningful interactions can occur between them. The horror of the heat death lies not just in its finality, but in its absolute cosmic bleakness. It represents a future where not only is life impossible, but where the very concept of change or event becomes meaningless. In this state of perfect thermal equilibrium, time itself loses all significance. With no change possible, there can be no arrow of time, no distinction between past and future. This endpoint of cosmic evolution challenges our deepest notions about the nature of existence. We tend to think of the universe as a place of constant change and renewal, where destruction is always balanced by creation. The heat death represents the ultimate refutation of this view. It suggests a universe that, in the long run, trends inexorably towards stasis and death. The philosophical implications of the heat death are profound and disturbing. If the ultimate fate of everything is to dissolve into a formless, meaningless void, what significance can we ascribe to our actions, our civilizations, our very existence? In the face of such cosmic futility, how do we find meaning or purpose? Moreover, the heat death raises troubling questions about the nature of information and memory in the universe. As the cosmos approaches perfect equilibrium, all traces of its prior states will be erased. The intricate structures and patterns that make up galaxies, planets, and living beings will be smoothed out into uniform nothingness. In a very real sense, the universe will forget its own history. This erasure of cosmic memory ties into deeper questions about the nature of time and causality. If in the far future, all traces of the past are obliterated, in what sense can we say that past ever existed? This line of thinking leads to unsettling philosophical territories, challenging our most basic assumptions about reality and existence. The concept of heat death also intersects with other areas of physics in ways that amplify its cosmic horror potential. For instance, some theories suggest that quantum fluctuations might be able to produce new universes or regions of order within the dead cosmos. This raises the disturbing possibility of a cyclic model, where new universes bubble up from the void, only to eventually suffer their own heat death ad infinitum. Another terrifying possibility arises from the intersection of heat death with the many worlds interpretation of quantum mechanics. If every possible quantum outcome spawns a new universe, then there might be an infinite number of realities all slowly winding down towards heat death. The idea of an infinite multiverse of dying universes adds an extra layer of cosmic dread to an already nightmarish scenario. Perhaps one of the most unsettling aspects of the heat death is how it challenges our notions of cosmic justice or purpose. Many human belief systems posit some form of ultimate meaning or judgment in the universe. The heat death suggests a cosmos that is ultimately indifferent, where all actions, good or evil, all achievements and failures, are ultimately erased in the uniform void of thermal equilibrium. The heat death also poses profound challenges to any notion of long-term survival or legacy for intelligent life. Even if a civilization were to master interstellar travel and spread throughout the galaxy, it would eventually face the insurmountable barrier of cosmic decline. No matter how advanced, no matter how resilient, life cannot outlast the dying of the light. This cosmic memento mori serves as a stark reminder of the fragility and preciousness of existence. In a universe doomed to eternal darkness, every moment of light and life becomes infinitely valuable. The very bleakness of the ultimate future throws the present into sharp relief, highlighting the miracle of our current cosmic oasis of complexity and life. Yet paradoxically, the study of heat death and the far future of the universe has led to some of our most profound insights into the nature of reality. It highlights the deep connections between fundamental physics, cosmology, and philosophy. It forces us to grapple with questions about the nature of time, entropy, and existence itself. Why does time flow in one direction? Why did the universe begin in a state of low entropy? Are the laws of physics themselves subject to change over these vast timescales? As we contemplate the heat death, we're forced to confront the limits of our understanding and imagination. The timescales involved are so vast, the conditions so alien to our experience, that we can barely conceptualize them. This cognitive vertigo, this stretching of our minds to encompass the unthinkable, is itself a form of cosmic horror. The heat death also raises disturbing questions about the nature of consciousness and subjective experience in a dying universe. As the cosmos cools and slows, would any remaining sentient beings experience time differently? Would consciousness itself become impossible as the energy required for thought becomes unavailable? The idea that awareness itself might sputter and die along with the cosmos adds a personal dimension to this universal horror. Moreover, the heat death intersects with our deepest existential fears. The idea of individual death is terrifying enough, but the heat death represents the death of everything. Not just all life, but all potential for life, all structure, all meaning. It is the ultimate cosmic grave, where not even memories or legacies can survive. As we conclude our exploration of the heat death of the universe, we're left with a mixture of awe and terror. This ultimate fate of the cosmos represents both the incredible vastness of time and the inexorable march of entropy. It is a reminder that the universe is not just stranger than we imagine, but colder and more indifferent than we can comprehend. In the face of such a cosmic endpoint, our existence seems both miraculous and utterly fragile. We live in a brief window of cosmic time where complexity and life are possible, a fleeting moment of light in an eternity of darkness. As we peer into the depths of the future, contemplating the long, slow decline of the cosmos, we must wonder, how do we find meaning in a universe doomed to fade away? What purpose can we ascribe to our actions, our lives, our civilizations, in the shadow of eternal cosmic night? The specter of heat death serves as the ultimate cosmic horror, a fate not just for us, not just for life, but for existence itself. It embodies the vast, impersonal, and ultimately fatal nature of the cosmos on its grandest scale. As we continue to push the boundaries of our knowledge, exploring the nature of entropy and the far future of the universe, the possibility of heat death looms large, a cosmic shadow stretching infinitely before us. In the end, whether the heat death turns out to be the ultimate fate of our universe or merely one possibility among many, its very conception highlights the awesome and terrifying nature of the cosmos we inhabit. It serves as a humbling reminder of how much we have yet to learn about the universe, and of the mind-bending possibilities that might exist in the depths of time. In contemplating the heat death, we confront a cosmic horror that challenges not just our existence, but our very understanding of what existence means in a universe winding down towards eternal frozen silence. The scale of the universe, cosmic insignificance. In the vast pantheon of cosmic horrors, perhaps none is more psychologically devastating than the sheer, incomprehensible scale of the universe and our own infinitesimal place within it. This chapter delves into the mind-bending vastness of the cosmos and the existential dread that arises when we truly confront our cosmic insignificance. To begin to grasp the horror of cosmic scale, we must first attempt to comprehend the vastness of the universe, a task that quickly overwhelms human perception and imagination. Let's start with our own cosmic neighborhood, the solar system. If the sun were the size of a grain of sand, the Earth would be about 30 centimeters away, roughly the length of a ruler. On this scale, the outer reaches of our solar system, where the Oort cloud resides, would be about 2 kilometers away. Already we're stretching the limits of what we can easily visualize. But this is just the beginning. Our entire solar system is but a speck in the vast expanse of the Milky Way galaxy. Our galaxy contains an estimated 100 to 400 billion stars. And if we were to scale it down to the size of North America, our entire solar system would be smaller than a grain of sand. The distances involved are so vast that we measure them not in kilometers or miles, but in light years. The distance light travels in a year, moving at an incomprehensible 299,792,458 meters per second. Yet even our galaxy, enormous as it is merely one among billions. The observable universe contains an estimated 2 trillion galaxies, each home to billions of stars and countless planets. The observable universe itself spans a diameter of about 93 billion light-years, a distance so vast that it defies comprehension. And even this may be just a tiny fraction of the entire universe, which could be infinite in extent. The horror of cosmic scale lies not just in these unimaginable distances, but in the existential implications they carry. In the face of such vastness, our entire planet, let alone our individual selves, becomes vanishingly insignificant. All of human history, all our triumphs and tragedies, our loves and losses, our grandest ambitions and deepest fears, play out on a cosmic stage so small as to be utterly invisible. This sense of insignificance is compounded when we consider the temporal scale of the universe. Our species has existed for a mere blink of an eye in cosmic terms. If we compress the 13.8 billion year history of the universe into a single Earth year, modern humans would appear only in the last 14 seconds of December 31st. Our recorded history would occupy less than the last second of the year. The concept of cosmic scale forces us to confront the possibility that we are utterly alone in this vast expanse. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them, takes on a new terrifying dimension when we truly grasp the scale of the cosmos. Are we alone because the universe is so unimaginably vast that civilizations are too far apart to ever contact each other? Or are we alone because life itself is vanishingly rare, a cosmic accident in an indifferent universe? Even if we're not alone, the scale of the universe presents nearly insurmountable barriers to any form of interstellar communication or travel. The nearest star system, Alpha Centauri, is over 4 light-years away. This means that even if we could travel at the speed of light, which physics tells us is impossible for matter, It would take over 4 years to reach our nearest stellar neighbor. Any signal we send into space, any call into the cosmic void, would take years, centuries, or millennia to reach potential listeners, with an equal time for any response. The vastness of space also implies that much of the universe is forever beyond our reach. Due to the expansion of the universe, galaxies beyond a certain distance are receding from us faster than the speed of light. This means there are regions of the universe we can never observe or interact with, no matter how advanced our technology becomes. Our observable universe is surrounded by a cosmic horizon, beyond which lies an unknowable expanse. This limitation on our cosmic perspective raises profound philosophical questions. If we can only ever observe a tiny fraction of the universe, how can we be sure that our theories about the cosmos as a whole are correct? Are we, as some philosophers of science have suggested, forever doomed to have an incomplete picture of reality? The scale of the universe also challenges our notions of uniqueness and specialness. For millennia, humans have placed themselves at the center of creation. We once believed Earth was the center of the universe. Then we learned we orbit the sun. Then we discovered our sun is one of billions of stars in the Milky Way. Now we know the Milky Way is one of trillions of galaxies. Each step in our understanding has further removed us from any privileged cosmic position. This decentralization extends to the realm of physics as well. We've discovered that the atoms that make up our bodies were forged in the hearts of long-dead stars. The iron in our blood, the calcium in our bones, these elements were created in stellar furnaces billions of years ago and scattered across space in supernovae explosions. We are, in a very literal sense, children of the cosmos. Yet this poetic notion is tempered by the realization that we are but one utterly insignificant expression of these cosmic processes. The concept of cosmic scale intersects with other areas of physics and cosmology in ways that amplify its horror potential. For instance, the theory of eternal inflation suggests that our observable universe might be just one bubble in an infinitely vast and eternally expanding multiverse. In this scenario, there would be an infinite number of regions like our observable universe, some nearly identical to ours, others wildly different. The idea that we might be one of infinitely many versions of ourselves, living out every possible variation of our lives, is both dizzying and deeply unsettling. Moreover, the scale of the universe has implications for its ultimate fate. As we've explored in previous chapters, the vastness of cosmic time means that we're likely living in the very early stages of the universe's history. The era of stars and galaxies, all that we can see when we look up at the night sky, is just a brief moment in cosmic history. In the far future, as the universe continues to expand and cool, it will become an ever more vast, ever more empty, ever darker place. The horror of cosmic scale also touches on our deepest existential fears. In the face of such vastness, how can our lives have meaning? If we are so insignificant on the cosmic stage, do our actions matter at all? These questions have haunted philosophers and theologians for centuries, but take on new urgency when we truly confront the scale of the cosmos. Yet, paradoxically, our ability to comprehend, however imperfectly, the vastness of the universe is itself a source of wonder and terror. We are, as Carl Sagan put it, a way for the cosmos to know itself. We are the universe become conscious, able to contemplate its own immensity. This self-awareness, this cosmic perspective, is both our greatest achievement and a source of profound existential dread. As we conclude our exploration of cosmic scale, we're left with a mixture of awe and terror. The vastness of the universe represents both the incredible scope of reality and our own cosmic insignificance. It is a reminder that the universe is not just larger than we imagine, but larger than we can imagine. In the face of such cosmic immensity, our existence seems both miraculous and utterly inconsequential. We are adrift in a vast cosmic ocean, our planet a tiny lifeboat in an unimaginably large and largely hostile universe. As we peer into the depths of space, grappling with distances our minds were never evolved to comprehend, we must wonder, what is our place in this vast cosmic tapestry? How do we find meaning in a universe so large that it renders all human endeavors microscopic by comparison? The specter of cosmic scale serves as the ultimate memento mori, a reminder not just of our individual mortality, but of the insignificance of our entire species, our planet, our galaxy, in the grand cosmic scheme. It embodies the vast, impersonal nature of the cosmos, a universe that is magnificent in its immensity, but utterly indifferent to our existence. As we continue to push the boundaries of our knowledge, exploring the nature of the cosmos and our place within it, the implications of cosmic scale loom large. They challenge us to find meaning and purpose not in some imagined cosmic importance, but in the very rarity and preciousness of our existence. In a universe so vast and largely inhospitable to life, the very fact of our being becomes a kind of miracle. In the end, the scale of the universe highlights both the terror and the wonder of our cosmic situation. We are inconceivably small, our lives fleeting beyond measure in the cosmic scale. Yet we are also the eyes and minds of the cosmos, the means by which the universe can contemplate its own existence. In grappling with our cosmic insignificance, we touch upon the most profound questions of existence, confronting a form of cosmic horror that is as awe-inspiring as it is terrifying. As we reach the end of our harrowing journey through the cosmos, we find ourselves standing on the precipice of understanding, gazing into an abyss of wonder and terror. We've traversed the darkest corners of the universe, confronted phenomena that defy our comprehension, and grappled with concepts that shake the very foundations of our reality. From the infinite void of space to the mind-bending implications of quantum mechanics, from the crushing gravity of black holes to the unraveling of space-time itself, we've explored a universe far stranger and more terrifying than our ancestors could have ever imagined. This final chapter serves not just as a conclusion, but as a reflection on our cosmic voyage and a contemplation of what it means to truly embrace cosmic horror. For in facing these cosmic terrors, we don't just confront the unknown, we confront ourselves and our place in the universe. The true essence of cosmic horror lies not just in the terror these phenomena inspire, but in the fundamental shift in perspective they demand. They require us to step outside our anthropocentric view of the universe and confront a reality that is utterly alien to our everyday experience. This cognitive leap, this stretching of our minds to encompass the unthinkable, is both the challenge and the gift of cosmic horror. Consider for a moment the dual nature of these cosmic terrors. The same stellar explosions that could obliterate life across light years also forge the heavy elements necessary for our existence. The incomprehensible vastness that makes us feel insignificant also provides the stage for the grandest story of all, the evolution of the cosmos. The quantum weirdness that defies our intuitions also opens up possibilities of technology beyond our wildest dreams. In embracing cosmic horror, we embrace the fundamental paradox of our existence. We are at once utterly insignificant on the cosmic scale, and yet, as conscious observers of the universe, we are also profoundly significant. We are the means by which the cosmos has become aware of itself. Our ability to comprehend these cosmic horrors, to study them and ponder their implications, is nothing short of miraculous. This perspective shift can be profoundly liberating. When we truly internalize our cosmic insignificance, many of our earthly concerns pale in comparison. The social anxieties, the petty grievances, the mundane worries that consume so much of our daily lives, all these are revealed as the trivialities they are when viewed against the backdrop of cosmic scale. At the same time, this cosmic perspective imbues every moment of our existence with profound meaning. In a universe so vast, so old, so full of wonder and terror, the very fact of our being becomes precious beyond measure. Every experience, every relationship, every moment of joy or sorrow becomes a unique and irreplaceable fragment of the cosmic story. Embracing cosmic horror also means embracing uncertainty. Many of the phenomena we've explored are at the very edge of our understanding, where our most advanced theories break down. The horizons of our knowledge are constantly expanding, revealing new mysteries, new terrors, and new wonders. To truly embrace cosmic horror is to become comfortable with not knowing, to find excitement in the unknown rather than fear. This acceptance of uncertainty is crucial not just for our understanding of the cosmos, but for our approach to life itself. In a universe where quantum indeterminacy reigns at the smallest scales, and chaotic dynamics can amplify tiny fluctuations into world-changing events. Certainty is an illusion. Embracing cosmic horror means embracing the fundamental unpredictability of existence, finding peace in the cosmic chaos. Moreover, the study of these cosmic horrors highlights the interconnectedness of all things. The atoms in our bodies were forged in stellar furnaces billions of years ago. The light we see from distant stars has traveled across vast gulfs of space and time to reach our eyes. The same fundamental laws that govern the dance of subatomic particles also shape the largest structures in the universe. We are not separate from the cosmic horrors we study. We are an intrinsic part of them. This interconnectedness extends to our relationship with each other and with our planet. In the face of cosmic vastness, the artificial divisions we create among ourselves seem petty and insignificant. The borders we draw, the conflicts we wage, the differences we magnify, all these fade into insignificance when viewed from a cosmic perspective. We are all fellow travelers on this pale blue dot, our fates inextricably linked. Embracing cosmic horror also means embracing our responsibility as conscious agents in the cosmos. We may be insignificant on the cosmic scale, but our actions have consequences. We have the power to shape our world, to explore the cosmos, to ponder its mysteries. With this power comes the responsibility to act wisely, to preserve and protect the precious oasis of life that is our planet, to use our understanding of the cosmos for the betterment of all. As we conclude our journey through the cosmic horrors of the universe, we invite you, our fellow cosmic explorers, to continue this voyage of discovery with us. The universe is vast and full of mysteries, and our exploration has only just begun. If you found value in this cosmic odyssey, if these journeys into the heart of cosmic terror have expanded your mind and sparked your sense of wonder, we encourage you to like this video and subscribe to our channel. By subscribing, you'll join a community of curious minds, united in our quest to understand the cosmos in all its terrifying beauty. Your support enables us to continue producing content that pushes the boundaries of our understanding, that challenges us to think beyond our everyday experience and confront the grandest questions of existence. Remember, in the face of cosmic horror, knowledge is our greatest ally. Each like, each share, each subscription helps spread this knowledge, fostering a global community of cosmic thinkers. Together, we can face the terrors of the cosmos, not with fear, but with awe and wonder. In the end, embracing cosmic horror is about more than just understanding the universe. It's about understanding ourselves. It's about finding our place in the cosmic tapestry, not as the center of all things, but as conscious participants in the grandest story ever told. It's about facing the darkness of the cosmos and finding within it a profound beauty. It's about looking into the cosmic abyss and instead of turning away in fear, diving in with curiosity and courage. As you go forward from here, carry with you the perspective that cosmic horror provides. Let it remind you of the preciousness of each moment, the wonder of existence, the interconnectedness of all things. Let it inspire you to live fully, to love deeply, to think broadly, and to never stop questioning. For in the end, we are all made of star stuff, children of the cosmos, bearers of the universe's consciousness. In our brief moments on this cosmic stage, we have the opportunity to contemplate the wonders and terrors of existence, to explore the greatest mysteries, to touch the face of the infinite. So let us go forward, not in fear of the cosmic horrors that surround us, but in awe of them. Let us embrace the vastness, the strangeness, the terror, and the beauty of the cosmos. For in doing so, we embrace the fullness of our own existence. We honor the precious gift of consciousness, and we participate fully in the grand cosmic drama of which we are all a part. Thank you for joining us on this cosmic journey. Like, subscribe, and keep watching the skies. For the greatest cosmic horror and the greatest cosmic wonder is yet to be discovered.